All right. Ladies and gentlemen, welcome to the first official episode of Page by Page. This is Engineering Today, and thanks for joining us. It's a fantastic Monday, June 18th, 2018, and today, the first official Page by Page stream. See, I'm sitting here in my lab. We had a good workout earlier. I've got my recovery protein right now. We're having a nice day. I was trying to finish up a little bit of simulator work before the stream, but didn't quite work out. We're still debugging. We're having a lot of fun, though. We're having a lot of fun. And here we are. We're back at the one, the only, Computer Organization and Design, RISC-V edition. An absolute chat favorite, to be sure. I know everybody is as excited as I am to start learning about computer architecture. Now, if you haven't seen the first two unofficial page-by-page streams, that's okay. We've got a great YouTube button right below that'll take you to my YouTube channel, and you can catch up on your own time if you like. But today we're going to start off strong, and we're going to start at chapter 3. It's okay if you didn't see chapter 1 and 2. A lot of these chapters are kind of, they cover a lot of different concepts in a lot of different areas. So you'll be okay. So let's go ahead and move on down to chapter 3. Chapter 1. Oh, here we go. We're getting close. We talked about the instruction set last time. But today is a focus on computer arithmetic. See, I like computer arithmetic. I took an entire course on computer arithmetic during my undergraduate degree. We had a lot of fun. Here we go. Arithmetic for computers. Let's get started, guys. Okay. So what we're going to do in this chapter, we're going to talk about how computers handle arithmetic data. We're going to talk about a typical size of operations within the computer called words, which are composed of bits, and how these represent binary numbers. Because as you guys know, computers are made out of transistors. So, if something's made out of transistors, those are just a bunch of switches. And if you just have a bunch of switches, well, you can only represent ones and zeros. Well, that won't do, because everything we use today, we think it's all in decimal, but we'll see how you can represent decimal numbers in binary. And then we'll go into how exactly we can start doing mathematical operations on these numbers. We've got some keywords here, don't worry. We'll go into those later. So let's break it down, what we're going to be going over today. It's a fairly short chapter. The instruction set was probably one of the longer chapters that we're going to get through. So after a brief introduction, we're going to talk about addition and subtraction, followed by multiplication and division. These are going to be the foundation of what we're going to be, of pretty much all operations in the CPU. But then we're going to talk about something equally as important, which is floating point arithmetic, based on the IEEE 754 standard. Then we're going to talk about some very interesting concepts like parallelism, specifically subword parallelism. And then we'll probably go over some of these extra sections, so some streaming, SIMD, and advanced vector extensions in x86. So this will be some modern stuff that Intel processors do. We're going to be going over how we can accelerate something like matrix multiply. If you're somebody that's a big fan of artificial intelligence or machine learning, this will be especially important to you. Most of pretty much all of machine learning really stems from this idea of matrix multiplication and linear algebra operations. Then, because this is a good old Patterson and Hennessy book, we've got to go over the fallacies and pitfalls. We've got to keep you guys from making those silly mistakes or thinking something that's not quite correct. And then finally, we're going to go over, see if they have anything interesting to say in the concluding remarks. We'll go ahead and skip the historical perspective and further reading for today. Perhaps on our own time we can do something about that. Okay, so just as a refresher, remember, we've got 5 key components of a computer. We have our inputs and outputs, we have our memory, we have our control, and we have our data path. So when we're talking about computer arithmetic, what we're referring to in a processor is usually referred to as the data path. So that's going to be our focus of today. So let's jump in. So computer words are composed of bits. We already knew that. So what do we want to know? We want to know, how about fractions and other real numbers? How are we going to represent those in a computer? What happens if we create a bigger number that can be represented? So let's say we have, 3 decimal places. So we can represent numbers from 0, from 0 to 999. What happens if we want to represent 1000? What happens if we get that as a result of some operation? Well, we'll see how we're going to cover things like overflows. And then underlying these questions is a mystery. So how does hardware really multiply and divide numbers? And I might be able to provide a little more insight into this. There's very cool designs of multipliers that we can do. There's things like carry array multipliers. There are shift over multipliers, all with this idea of balancing the area cost of putting down transistors with the speed cost, and exactly how fast we can get these operations to run with the minimum amount of gate delays from input to output. And so that's usually called the critical path. It's the maximum amount of time that a circuit takes to complete some operation. Okay, so what we're going to do is we're going to unravel these mysteries. So let's go ahead and let's jump right in. So let's go ahead and handle addition and subtraction. So addition is just like you would expect in computers. Digits are added bit by bit from right to left. So we already know a lot of this stuff. This is the same thing that we do every single day if we're doing addition. So subtraction uses addition. Aha! So if we add a negative number, that's pretty much how a computer, or that's not pretty much how, that's exactly how a computer does something like subtraction. We just see it in the machine as an addition operation. We just need a number system that is able to support that. And that number system we're going to call 2's complement. So in normal binary, let's start at decimal actually. Let's start at decimal. So in decimal, if we had a number like 123, we can say that this is exactly equal to something as simple as 1 times 10 to the 2 plus 2 times 10 to the 1 plus 3 times 10 to the 0. And if we work this out, we get 100 plus 20 plus 3, which is 123. Now, what happens the other way around? So, if we take this, what happens if we want to do something like binary, which is base 10? So if we look at the first term of the decomposition of 123, we see that it's 1 times 10 to the 2. So when we say base 10, it means that these are always going to be powers of 10. So likewise, it stands to reason that if we were going to do something like binary, and we had, say, a pattern like 1, 0, 1, it would follow the same pattern. So this would be 1 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0. So this is going to be 4 plus 0 plus 1, which is 5. So we see here, this right here is the binary representation of 5. Pretty neat. Now this still hasn't answered the question of how do we represent negative numbers. So with a minor addition, a minor change to this weighting system, we can represent any negative number that we want to. So what I'm going to do is something called 2's complement. And that says that if we take a number like 5, so we'll use 4 bits this time. So if we do something like 0, 1, 0, 1, which we just added a 0 out in front, so that's not going to change anything. If we flip all the bits, it becomes 1, 0, 1, 0, and then we add 1, we get 1, 0, 1, 1. Now, this may seem confusing at first, because if we were to take this number at face value, let's write this over here again. So let's write 1, 0, 1, 1. If you were to compute the face value of this number, it's going to be the same as 1 times 2 to the 3 plus, let's write that 3 better, plus 0 times 2 to the 2 plus 1 times 2 to the 1 plus 1 times 2 to the 0. And if we add this together, we get 8 plus 0 plus 4 plus, oops, did I miss something? It's plus 2 plus 1. So this is going to be 11, right? 11. 8 plus 2, 10 plus 1, 11. Well, that's not negative 5. So how does this make any sense? And so what it turns out, all we have to do for this to make sense is we make this first power negative. And as soon as we do that, we get what's called 2's complement, where suddenly we have a way of representing arbitrary, we can represent any negative number we want to just by changing this weight. And so what we get here ends up being negative 8 plus 0 plus 2 plus 1, which ends up being negative 8 plus 3 is equal to negative 5. So now that we have this number system, basically understood, let's go ahead and see exactly how they're doing this kind of calculation. So down here we have 7 plus 6 is equal to 13. Very simple operation. And so let's see exactly how we would do this in a computer, or how we would do this in binary. And so it works basically the same. So we start out right here. This first place, we're adding a 1 and a 0. So 1 plus 0. Okay? Remember, this is all base 2, so we can't get numbers like 2, 3, 4, 5, 6, 7, 8, 9. These all have to be 0 or 1. So that means if we get 1 plus 1, that means we have a carry of a 1 and a sum of 0. So here with the carries, up here, so for the first one, for the first sum, 1 plus 0 is 1, so we get a sum of 1. Over here, we didn't carry anything, and so we look at the next two digits, 1 and 1. So we add 1 and 1 together. We get 0, but we get a carry this time. The carry goes up here. We get 1 plus 1 plus 1. Well, we know 1 plus 1 generates a carry, so we'll put the carry out here. And then we have a single 1 left over down here. And so we continue through this, and we end up with a sum of, if we consider that all of these upper bits are all 0, and we're really only adding these lower 4 bits together, those are the only ones that really have any value, we see that we end up getting a final sum of 1, 1, 0, 1. And then we have a bunch of zeros out here. And so if we do a quick sanity check, this is going to be 2 to the 3. This is going to be 2 to the 2. This is 0, so we'll just add 0 there. And this is going to be 2 to the 0. And so we get 8 plus 4 plus 1. So we get 13. Okay. It's pretty simple. I think we get it. I think we can move on. This is a pretty simple subject. Now, we can go the same way with addition, or we can go the same way with subtraction as we did with addition. So we already know that, normally when we think about it in a real world scenario, if we're doing this on pen and paper, not in a machine, we can do the same subtraction rules apply. We can do the same borrowing from one place to another. So in this case, if we're doing 7 minus 6, if we have 7, 1, 1, 1, minus 6, so minus 1, 1, 0, we know that this is going to be 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 1 is 0. So we get a result of 1. Pretty simple. However, it's more useful for us to think of it in that idea of 2's complement that we looked at earlier, where step 1, we flip all the bits, and we step 2, we add 1. And that's exactly what they did to this bottom term. This is still negative 6. They're still subtracting, but this time the operation is doing binary math by hand. Listen, sometimes you have to do it, Cute Berry. Sometimes you have to do that binary math by hand. Sometimes that's the best way to understand it. And so here they do the same addition. It looks a little more complicated here. We're not going to write down all of these sums, because what we're going to see is we're going to end up with the same answer of 1 over here. We're going to see that these two ones, we'll go ahead and zoom in so we can see this a little bit better. So what ends up happening is this one and this one generate a carry that goes all the way through and eventually gets discarded at the very end. So pretty simple. And so that last bit that kind of flies out, we usually call that the overflow bit, because it overflows the space that we have. We don't have enough room to store all these bits, so we have to get rid of some. Now in the case of subtraction, this is fine for us. This is actually perfectly fine, because we don't care about this bit that goes out. In fact, the number system is actually makes this work. So we can go ahead and move on, and we can go ahead and see what else they have in store for us. So we're adding on different signs. Okay. So here we're talking about, of course, 64-bit operations. So we have 64 bits of A, 64 bits of B, and we have a sum of 64 bits. Now the reason why we have this system in place where everything's 64 bits is because when we're designing hardware, it would be really, really complicated if we were to design hardware that was all differently sized. And so we'll see later that when we're actually manufacturing hardware, consistency and regularity is something that we really want to emphasize. So here we say, when can overflow occur in addition? So one key thing to note is that when we're adding with different signs, so a positive and a negative, or a negative with a positive, we can never get an overflow. It's not possible. Now, when they're the same size, that's when we can get an overflow. And so we can prove to ourselves why we can never get an overflow. And we can do it with a very simple example. So let's take 3 bits. So let's take the maximum negative number we can have, 100, which is -4. And let's take the largest positive number we can have, 0, 1, 1. And so this is going to be 3. Now, for any combination of negative and positive numbers, we'll see that we'll never exceed the bounds of -4 and 3. So if we have -4 and 0, and we do this addition, we get -1, well within our bounds. Now, if we take the opposite example, where we do the smallest negative number, -1, and we add the largest positive number, 3, we get 2. So we see that, we can kind of just prove to ourselves by this quick example that when we have different size, we can never get an overflow. Okay, so let's move on. Fairly simple stuff. Okay, let's see what they're talking about here. They're simply reminding us that subtraction is the same thing as adding a negative. And so then we get to this point of knowing when an overflow cannot occur in addition and subtraction is all well and good, but how do we detect when it does occur? So clearly adding and subtracting two 64-bit numbers can yield a result that needs 65 bits to be fully expressed. The lack of a 65th bit means that when an overflow occurs, the sign bit is set with the value of the result instead of the proper sign of the result. Since we need just one extra bit, only the sign bit can be wrong. Hence, overflow occurs when adding either two positive numbers and the sum is negative, or vice versa. And so, just by a quick example, we can prove the reverse. So if we have something such as 0, 1, 1 plus 0, 1, 1, so this is 3 plus 3, what we end up getting is this will be a 0, we'll carry a 1, this will be a 1, we'll carry a 1, and then this finally will be a 1. Okay, so this number right here, if we remember that it's a signed number, this largest binary weight will actually be negative. So this is going to be -4 plus 2 is going to be equal to -2. Well, we know that 3 plus 3 is of course not -2. So what's going on here? So if we did have that magical extra bit, that means this 0 would be the negative number. So it would be a -0, this would be a +4, and we'd have our correct answer of 6. So we proved with the positive case we can make an incorrect result by adding two fairly large in terms of the number of bits we have. We can prove that we can get that overflow in that case. And then I won't prove it here, but the reverse is true. If we do two significantly large negative numbers, we can also get the same type of overflow. And so here we just have a table giving this kind of proof. Okay, so let's move on. Let's see if there's anything else interesting. So in Appendix A, the key piece of hardware that does all of this kind of math is something called an ALU, which is an arithmetic logic unit. Oftentimes it's denoted looking like this. Sometimes people will put a plus on it if they're talking about purely addition. Sometimes they'll put some other symbol on it. But the basic idea is that you have all your inputs coming in, you have an output, and then you have some line out here. You have some wire connected to here that's a select. And this basically says, okay, do I want to do addition? Do I want to do subtraction, multiplication? Do I want to do division? What do I want to do today? And so that's what Appendix A is going to go over. So an ALU is hardware that performs addition, subtraction, usually by logical operations such as and or. It doesn't have to just do these two specific operations. It can do much more than that. But a lot of the times we have dedicated multipliers, so that's why they bring it that way, or they present it in this way. So hardware and software interface. The computer designer must decide how to handle arithmetic overflows. Although some languages like C and Java ignore integer overflow, languages like Ada and Fortran, basically languages that we don't care about, require that a program be notified. Ada was a Department of, if I'm not mistaken, Ada was a Department of Defense built language. And then Fortran's just a very old language as well. You'll see a lot of oil and gas companies, I think, still use languages like Fortran. Mainly because they have giant code bases of like 1 million lines of code that it would cost too much money to kind of to update. Okay, so we have a check yourself. Some programming languages allow 2's complement integer arithmetic on variables declared byte and half, whereas RISC-V only has integer arithmetic operations on full words. So this basically says that if we're going to do an operation, Rip Cassini programmers. Yeah, that's true. So this basically just says that in RISC, when we're going to add and subtract numbers or signed numbers, they have to be the full 32-bit signed numbers. We can't do any funny tricks where we're doing 8-bit or 16-bit addition. RISC-V basically says, okay, you can only do it on 32-bit. Okay. So there's also this key idea of saturation. And this basically says, now, we're not going to lose all the data when we roll over. And so what I mean by lose all the data is if we go ahead and do something such as take, 1, 0, 0, so a very large negative number, and then we make it even smaller by adding something like just 1. What this generally means is that this end result of 0, 1 that suddenly turns positive, usually what happens is this will remain simply at the largest negative number possible. Now, so they do a good example here. If you have a volume knob and you keep turning it, you wouldn't want every time you turn it all the way to the right, it suddenly, the volume shuts off, and then you have to go turn it even more and it goes up and up and up. But if you passed a certain point, it suddenly gets quiet again. Now you wouldn't want that. So that's the idea of saturation. It basically says that if you keep increasing past a certain point, it's not going to change the number anymore. The number will stay constant. So now we can move on to something that's a little more interesting, multiplication. However, it's still fairly simple. So this is a funny quote. It says, multiplication is vexation, division is as bad. The rule of 3 doth puzzle me, and practice drives me mad. So apparently this person, this Elizabethan era person, didn't like math too much, but I'm not sure why. Multiplication is fairly easy. Now division we probably won't go into too much, but division is actually incredibly difficult in computers, and the hardware is incredibly complex. But we see that when we're doing something like multiplication in binary, it's actually fairly simple. It's even simpler than it is in decimal. So what happens is, if we have a 1, we copy down this top number. We just do a copy. And if it's a 0, we just skip. And we do the same shift every single time like we do in regular multiplication. So in this case, I think they're doing unsigned multiplication. So this is just 8 times 9. So the first one they copy down, like I said. The next two are both zeros, so all they do is shift, shift, and then the final one they copy down again, 1 0 0 0. Fairly simple. And then after every single clock cycle, so that you can think of these being calculated per clock cycle. So this would take 1 clock cycle, 2 clock cycle, 3 clock cycle, 4 clock cycle. And this bit is finalized first, this bit is finalized second, this bit is finalized third, and then after this many clock cycles, all of these guys, these remaining bits get finalized. Okay. A fairly simple example. We have the multiplicand, of course, up here, and we have the multiplier down here. Just some naming conventions that can be useful. How's everyone doing? Everyone still doing well? Listen, it's a wonderful Monday. I'm glad you're all here. We're going to have a great time today. I have a new schedule now. If you look right below the stream, I've got the schedule. If there's certain topics you're interested in, feel free to come on those days. Weekends are going to be more relaxing. We're going to do some stuff like learning new languages and then maybe having some fun on Sunday. Okay, so let's continue on. The first operand is called the multiplicand, and the second the multiplier. The final result is called the product. Okay, we can skip most of it, as I think we know this. So let's look at a sequential version of this multiplication in hardware. So this will be a very, very simple multiplier. In reality, we can design much faster ones, but we'll leave that to a different stream. So let's see what happens. So we have the multiplicand, and if we remember what the multiplicand is, that's going to be the top number. This is going to be a number that we're multiplying by some multiplier. So we're basically, if we were to speak this in our general spoken language, we would say that this is 8 9 times. So it's going to be 9 eighths. So what happens here is we have a shift right over here that basically will go through all of these bits of the multiplier, deciding whether or not we're going to copy the top number. And that's going to be this control test. This will basically test if equal to 1 or equal to 0. And so we'll put the entire multiplicand here. We will put the product in here. So this product is going to be initialized at 0. And we're going to add. Okay. Pretty simple. Now, on the next iteration through, we do the same test. This time, the multiplicand shifts 1 over to the left. So if we started with something like 0, let's look at an 8-bit number. So 0 0 0 1. So we start here. It'll be 1 times some number over here. Let's do 1 times 5, or 1 times 2. Okay. So we have something as simple as 1 times 2. So the first time around, it's a 0. As 0 goes into our control test, we don't write anything this time. 0's here. We stay at 0. The multiplicand comes in, but we're not writing anything, so nothing happens essentially. Now, next, what happens is we shift over 1, and the multiplier shifts 1 over to the right. So the next time around, these numbers get rewritten. Now, we copy this number down into the multiplicand. Then, this goes in here. Our product is still coming in as 0 because we didn't do anything last cycle. We do this control test. We do write this time. And then this goes in. We do this number, which is 2 plus 0. Our product ends up being 2. And then that ends up getting written. So we do one more shift. This gets shifted to the right. That goes away. And we see that we have zeros for the multiplier for the rest. So we see for the rest of the time, this right's going to be disabled. So we're never going to be changing this product again. So we did a little proof that said if we multiplied 1 by 2, we went through when we saw how this would flow in real hardware. Any questions on that? I think that should be fairly straightforward. If we were to look at this, how it would look on paper, if we did 1 times 2. So even if we just looked at the lower 4 bits, it would be 0, 0, 1, 0, and or 1 times 2. 0, 0, 1, 0. The first time it would be 0. This left shift of the multiplicand is the same thing as shifting over here. This time we're going to copy, so it's going to be 0, 0, 0, 1. And so we see we get 2. Pretty simple. Okay, moving on. Now we can also do a little bit, there's an important note here. So we saw everything earlier was 64 bits, and so we have to think of ourselves, well, why do we have a 128-bit ALU? Why would we need that for 64-bit operations? So let's think about the absolute maximum number that we could get when multiplying. So if we take something such as unsigned numbers, 1, 1, 1, 1 times 1, 1, 1, 1. This is the largest for 4 bits that we can get. This is the same thing as 15 times 15, which is 255. Oh, sorry, it's not 255. What am I thinking? It's 225. Right? Yeah. Now, how much space do we have for 8 bits, though? Or what's the maximum number of bits that we need to represent this? So 2 to the 0 is going to be 1. Okay, so we need more than 1 bit. Let's skip a couple. Let's go to 2 to the 4. So 4 bits. This is 16. Still not going to work. Let's go to 2 to the 6. So this is going to be 64. 2 to the 7th, 128. 2 to the 8th, 256. So we see that with 8 bits, that's the minimum of number of bits we can get away with to do a 4-bit times 4-bit multiplication. So what we see that is for multiplication, we need 2n bits for the result. So if we're multiplying two 64-bit numbers, we need a minimum of 128 bits. So that's an important thing to keep in mind, so we can design our hardware around that. Okay, let's move on. This was pretty easy. We basically just did addition again. We did addition with, now we did some shifting, so we got a little bit fancier with our tricks. But at the end of the day, it's still addition. Don't forget, guys, if you like the stream, go ahead and give me a follow. I've got the new schedule down below. We've got great content coming. Tomorrow's going to be a course on compilers. I'm excited. I'm going to be taking compilers as one of my qualifying exam subjects on August 15th. That's when that test is. I've got to get ready. I've got to prep. So I'll be prepping with you guys. Okay. So here we have, so they just do some block diagrams, and this is what we went over already. Okay. So we did this already. Great. We got through a lot of content with that example. So sign multiplication. So we only did positive numbers there. So what happens if we want to do something that's signed? This is interesting. So let's see. So what do they do? Okay. So they only speak about a very simple way to do multiplication of signed numbers. And it's this kind of idea that we can call a patch-up method, where basically we take two numbers, say we're doing, if we want to multiply 6 times 6, we multiply them together, we get 36. We ignore the fact that maybe the top one is negative until the very end, and then we say, okay, now it's negative. So in binary, what this would look like is something very simple, such as if we did 3 times negative 3, or let's do something even more simple. Let's do 2 times negative 1. So here we would do 2 or sorry, no, negative 1 times 2. Or 1 times negative 2. There we go. That's the right one. So we have 2 times 1. We multiply these together. 0, 1, 0. We see that for the rest of the results shifted over, they're just going to be zeros. So our final result is going to be 0, 1, 0. Now, this patch-up method says, okay, just do the unsigned, and then at the very end, what we'll do is we'll flip all the bits, 1, 0, 1, and add 1, 1, 1, 0. So they do this conversion to a negative number at the end. So remember, this is negative 4 plus 2, or negative 2. That's this kind of patch-up method. So they don't go into the interesting ways of doing multiplication. Or they might. So let's see what they mean by faster multiplication. So Moore's Law. So Moore's Law is something that we talked about earlier. It basically says that every 2 years, transistor size decreases by 1/2 and gets half as expensive. So it becomes twice as affordable. So you can basically have twice as many transistors in the original area that you had before. So let's see. So how would we build a faster multiplier? Okay. Here we go. A very interesting way. So this is something called a carry save adder. So instead of doing instead of doing this very programmatic, very serial way of going around in a loop over and over and over again for 64 iterations, so for all 64 bits of the multiplier, what if we just did a giant tree? That makes sense. So basically, they break down the multiplication into lots of additions, an entire giant tree of additions. And instead of having to wait a super long time, 64 iterations, they can get away with a logarithmic scaling on this. So instead of saying for something like 64-bit multiplication, they can get away with a timing of log 2 of 64. And so that's going to be, if I'm not mistaken, 8. Because 2 to the 4 is 16. That means 2 to the 5 is 32. 2 to the 6 is 64. Okay, so it's actually 6. So they only have to wait, 6 addition times in order to calculate something that we previously had to wait 64 cycles for. So way better, way better. But as you can see, over here, what's our cost? What's the cost of our hardware? We have a single ALU. We have this single product buffer. We have this very simple control test. Remember, this is just a zero. This is a simple OR, right? This is something ORed with 0. This is 0 ORed with some bit A coming from the multiplier. And we have another buffer up here to store the multiplicand. And then we just have some wires, right? Now let's look at the cost of this big carry save adder. Now we don't have a 128-bit ALU, but look here. We have tiers and tiers of adders now, 64 bits with all the interconnects. Very expensive, but very fast. It's not the fastest, I don't think, but it's very fast. Okay. So multiply in RISC-V. Okay. So this just says some of the instructions that we could use for multiplication. We can do multiplication of the entire, to get an entire 128-bit product, or we can do kind of a half multiplication to get a 64-bit product. Very simple. So summary, multiplication in hardware is a bunch of shifts and adds. Very simple. And it looks in hardware the very same way that it does on paper. So it's the same idea of shift and add, shift and add, shift and add. That's the key idea when it comes to multiplication. And then the very key, one of the key ideas with fast multiplications is that we can do all this work in parallel. Okay. I like it. I like where we're heading. I'm getting some good foundation in. So division. Let's look at division for a little bit. So, of course, it's a reciprocal operation of multiplication. However, it's very difficult. It's very difficult for a computer to do. And all that we need to do to see why it's very difficult is let's look at a simple division of, say, 18 divided by 4. Now, if we were to do this, we would say, does 4 go into 1? No. Okay. How many times does 4 go into 18 now? Okay, that's simple. It goes in 4 times. Minus 16, remainder of 2. However, we notice that we skipped an important step here. If we were to design hardware, we skipped a very important step. So if we remember when we're doing addition, we saw that it was very programmatic. So if we had something like 0, 1, 1 plus 0, 0, 1, what do? We take 2 bits, we add them together and we do a carry. We take these bits, we add them together, we get a carry. We take these bits, we add them together, we just get a sum. Now, we saw in this division though, where we had 18 divided by 4, we take these two numbers, this 4 and this 1, and we compare them. We skipped over that part. We didn't write anything down when we compared these. But some operation had to happen here. And so that operation is, of course, always subtraction. So the operation we're doing in our head is we're doing minus 4 here. We're testing this. We get negative 3. We go, uh-oh, we can't get a negative number here. Division, when both numbers are positive, has to be positive. So what we end up having to do, that we also do in our head, is we add back. So now that we see we're incurring this cost of every single time, if we make a mistake, we're incurring both a subtraction penalty and then potentially a corrective addition penalty. So very, very dangerous. It's something that you don't always think about, but that's what makes division so difficult. And when we're talking about these scales of operations, so addition and subtraction, we can get done in roughly 1 to 2 clock cycles in modern machines. Now, multiplication, roughly 2, maybe 4 clock cycles. Because as we saw before, multiplication is really just division. Or multiplication is really just addition. We're just adding a lot of things in parallel. Now let's look at division. Now this is the surprising thing. This generally takes on order of 500 to 1,000 clock cycles. Very, very slow. And it's because we don't have a lot of fast ways to do this. We see that we have to do this corrective measure every single time. Even the best types of dividers are very slow for this reason, because they still have to do this kind of checking. There's very optimized ways of doing this by having things like lookup tables to figure out whether or not you're going to have to correct or not, and automatically get a temporary result. However, it's still very slow compared to something like addition, subtraction, and multiplication. LSL operators? What are LSL operations? Or operations? ATIONS. Logical shift operations. Okay. So with multiplication, the biggest overhead you're incurring over regular addition is you'll maybe have some shifts. But with division, you're going to have those shifts. You're going to have subtractions to compare numbers to see if one is bigger. Then you're also going to have additions to correct in case that number was bigger. So take this scenario. In our head we go, is 4 bigger than 1? Now what we're doing in our head is we're going 1 minus 4. Is that negative? Yes. Skip over. So what we have to do in a computer though, because this has to be done in hardware, a computer can't think. It only has, circuitry. So what does it have to do? It has to go, okay, 1 minus 4, negative 3. Is this negative? Yes. Add back, correct. And then we get 1 again. And only then do we shift. So just to do this single operation to get past here, we have 3 steps. We have a subtraction, an addition, and then a shift. So that's why division can be so slow. So let's look at some basic ways of doing division. Now, I think they take the easy way out in this book. I don't think they go into the hardware. Okay, they do go a little bit. They go into a very dumb divider, an incredibly slow divider. Okay, so we see that just like all the other operations, we can do the exact same thing, right? We can do the exact same thing when we're doing division as we did on pencil and paper for something like when we did this 18 divided by 4. We see that we can go, okay, well, this is 0, right? And then we can we can go over, and so then we can go, okay, this goes in 4 times 16, and we get a remainder of 2, right? We see that we can do this on pencil and paper, and that's more or less what they're doing here. So all that they do here is they test to see if these 4 bits are bigger than these 4 bits. They are. 1001 is bigger than 1000. They do a subtraction, so this bit turns to a 0. This is already a 0. Then they get 0, 0, 1, 0. And basically what they do is they just do a ton of shifts. They just shift over a bunch. They shift over 2 times here until they get 1, 0, 1, 0, which is a number that they can subtract again. They subtract, they wind up with 1, 0, and no bits left at the end. So this ends up being the remainder. Now remember, this is in a remainder of 10. Okay, it's base 10. This is weird that they would do it this way. This book has some problems doing things in like base 10 when they should be doing it in base 2. I'm not a big fan of that. But we see that on paper we can do that, but the hardware is more interesting. The hardware is much more interesting. So let's see what they try to do. Okay. Do they have some kind of oracle that tells them if it's going to lead you to a positive or negative remainder? Let's see. So figure 3.8 shows the hardware to mimic our grammar school algorithm. We start with the 64-bit quotient register set to 0. Each iteration of the algorithm needs to move the divisor to the right 1 digit, so we start with the divisor placed in the left half of the 128-bit divisor register, and shift right 1 bit each step to align it with the dividend. The remainder register is initialized with the dividend. Sure. Okay. Okay, so they do this very, very simple, way of doing division here. This is actually incredibly unrealistic to real hardware. I wish I had a good picture in front of me of how to showing how we actually do division. I'll show it later, but basically we can do this on paper with maps. We can use these nifty little maps, and basically we'll have our bounds of our upper bounds, and we'll have some positive and negative bounds, and we'll do division, and then depending on where we get here, we'll do subtraction, and we'll go here, then we'll do a correction, and then we'll go here to some amount after we add that, and maybe we'll get some correction. And so there's some incredibly interesting division algorithms we can go over. But here they implement the hardware to do the grade school shift over if it's big enough, and then simply add. And by add I mean subtract, adding a negative number. Okay. So let's go over the algorithm they're talking about. So at start, they subtract the divisor register from the remainder register and place the result in the remainder register. Then they do this test like we talked about, that basically says, okay, was this number, pin's not working. Interesting. So, as we know, they do this simple test. If it's positive or negative, they add back over here if the remainder is negative, If it's positive, they just shift over, setting the rightmost bit to a 1. And then they time this out to check if we need to go back to the beginning, if we haven't gone through all the bits yet. And then finally, they finish. So some pretty simple stuff, not terribly complex. Now, for some reason, I'm not getting any... I'm not getting any... Let me go ahead and restart this program. It's not wanting to save. It's not liking this right now. So let's go ahead. Let me open this again. Okay. Open. Computer organization. Okay. Let's go back down to where we were. The front end. This is 2. Here we go. There we go. Okay. Okay, I can write again. That's good. Some technical difficulties, but we're back on track. Okay. So here they go through another example of using the divide algorithm, and they go down at every single point exactly what it looks like. So we can look through a couple of these. So initially the quotient, of course, is 0 because we haven't divided anything yet. The divisor is, let's see, this is 8, 16, 32. And then the remainder that we're going to be dividing by is we're pre-initializing this. Okay. This is a divisor, and the remainder is going to be is what we're dividing. So 0, 0, 0, 1, 1, so this is going to be 7. So this is going to be 32 divided by 7. So what they do is this initial subtraction. They get a negative number. So after they get a negative number, they correct back, and look, we took these 3 cycles, and we're back to the beginning. Okay. So we basically took some time to do nothing. They do some shifting. They shift this over. They do another subtraction. They get a negative number. So they have to correct for it in the next step. And then they move over 1. So they do another shift. Then they have this again. They do another subtraction. They get a negative number again. They have to correct. They shift over even more. They try it again. This time it's a positive number. They add a 1 to the quotient. They do another shift. They do another subtraction. It's positive. They add another 1 to the quotient. They do another shift. And then they're finished. They know that they can't go any further, so it's finished now. So, pretty simple. So this is an example, yeah. This is a fairly simple example. But that's this idea of correction and why division is so slow. So let's look at how many wasted cycles there were here. So this is a wasted cycle, this is a wasted cycle, this is a wasted cycle. Okay, so let's move on. So this algorithm and hardware can be refined to be faster and cheaper. The speed up comes from shifting the operands and the quotient simultaneously with the subtraction. This refinement halves the width of the adder and registers by noticing where there are unused portions of registers and adders. This shows the revised hardware. So basically they seem to split this, and then they have additional control tests that say we can predict when we need to shift left or right, and we also have the control of when we're actually writing. Fairly simple. So sign division. So sign division, they take the easy way out. Sign division, they say, okay, we ignore the fact that there's a negative number, and then at the very end, we modify it. We make our result, our quotient, negative. Pretty simple, but it's cheating. They're a bunch of cheaters. Okay, so faster division. Let's see if they get into anything interesting. So Moore's law applies to the division hardware as well. So we want to scale with more transistors. We want to build faster hardware. And we especially want to target something like division. So we would like to be able to speed up division by throwing hardware at it. We used many adders to speed up multiply, but we cannot do the same trick for divide. And this is that sign difference that we were talking about. So there's a technique that we use to produce more than one bit of quotient per step, and this is SRT division. So SRT stands for the three guys that invented it. I forgot their names. Let me look that up real quick. SRT division, it was Sweeney, Robertson, and Tosher. I think one of these guys also invented or two of these guys were on the same paper that did a fast multiply. And so what this basically does is it predicts several quotient bits. So it says, okay, well, if I get something wrong, I don't want to correct right away. Let's see how far I can go before I pass a threshold, and then I'll do all the correction at once. So let's see if they showed this at all. Okay, so they basically this is just basically about prediction. This isn't entirely true. So they're not necessarily predicting whether they need to shift or not in the SRT division. It's not about prediction. That's this is actually this is actually wrong. In SRT division, you're basically just grouping up all of your operations into one big operation. So it's not necessarily what I would call prediction. And then they said that instead of actually having to calculate the numbers, you can basically have it in a big table. And so you can basically look up the answers instead of calculating them. This is an interesting idea. So if we were to design very, very fast hardware to do very basic operations, multiplies, adds, divides, subtracts, could we, if we had a sufficiently large table, could we look up the result faster than we can calculate the result? That's an interesting idea. My intuition says for addition and multiplication and subtraction, the answer is no. However, I think for something like division, because it takes 500 to 1000 clock cycles already, I think you could get away with it. I think you could. I think it's slow enough where you could make a case. And I think, like they said, they already use lookup tables. So I think that's probably the only arithmetic operation where that helps. So divide and RISC-V. So let's see how they do division. Okay, so they just go over. So they have a div instruction. They have an unsigned div instruction. They have a remainder instruction and an unsigned remainder instruction. So I'm not sure. These might just be for getting the remainder of a division or checking to see if a remainder is 0. To see if it's a positive or negative remainder, or if you're doing unsigned division, an unsigned remainder. I'm unsure what you would use those operations for, though. That's interesting. Okay, let's move on. So hardware and software, let's do a brief overview of this, see if there's anything interesting. So RISC-V divide instructions ignore overflow. So software must determine whether the quotient is too large. Okay, so there's basically saying that there is no hardware to do this detection, so it's a very naive. It's a very RISC-V is fairly naive, which it was developed by Berkeley. Not a knock against Berkeley, but it is an educational architecture, which means not, it doesn't have a lot of features. Okay. Let's move on. Okay, so then they go over some of the common arithmetic instructions. We've got our adds, we have our shifts, we have our multiplies, we have divides. Now, keep in mind that we do something like a multiplication. Down in the hardware, it's doing things like shifts and adds. Same thing with division, shifts and adds. And this is the same instruction set that we saw before with branching, with other shifting, with logical operations like or and ands, and then how we manipulate data with our loads, or how we load data and we access our data with loads and stores. So a lot of times this von Neumann architecture, sometimes people call it a load store architecture, or this is like the most common type of instruction set architecture. It's called a load store architecture, and it's basically under this idea that when we're doing things with memory, we're loading things from memory, and then we're storing results back to memory at some point. Okay. So floating point operation. Okay. So we're going through this chapter fairly quickly. Does anyone have any questions or any thoughts? Anyone excited? Let's see. We're probably going to have some time at the end of this. I had scheduled 3 hours, and I think we're over halfway through, and we're only an hour in, so we're going to have quite a bit of time at the end. So let's see. Let's go ahead and start with floating point, though. Dash, you're excited? Nice. Hi again. Are you going to show practical examples like in Verilog or something? We can do that. Well, I can. I don't have anything on this. I don't have anything like Vivado, or what's Altera's software. I don't have that software on this computer. Are we learning stuff today? Feels good, man. Yeah, man. We are learning stuff today. Listen, JB Pratt, Kamikaze Chicken. Listen, guys. Tell your friends. Get more people in here. Get as many people in here as you can. Follow the channel. Yeah, so Hitting Live, I can pull up some code after we finish going over some of this, and we can see how this stuff is implemented in hardware. Some other time, probably on Sunday, since that's... so if you look at the schedule below, you'll see that I have Sunday basically reserved for any kind of things or like fun stuff. And so I leave that as basically, okay, if there's any questions throughout the week, we can go over something. So yeah, so we could do something like that, and we could go over how would we design this if we were to want to design an integrated circuit that we would send off to a fab. What are the tools we would use, and how would we do that in hardware? But I can, at the end, after I get through this chapter, I can pull up some like Verilog code. I don't know VHDL, and I actually really dislike VHDL. So we'll look at Verilog. Eventually, I'll probably do. I have a advanced digital design using Verilog book. We could do an episode of page by page using that book. That will be later on after I finish these books. I think this book is only about 6 chapters or so, and we've already gone through 3 after today. So that means in about 3 weeks I'll be needing another book to do, so we could potentially do that book afterwards. But let's go ahead and move on. So we can look at some Verilog code at the end of today. So going beyond signed and unsigned integers, programming languages support numbers with fractions called reals. So basically what we're saying here is like the first computer EDVAC. The first stored program computer EDVAC was designed to calculate like ballistic artillery tables for the U.S. Army like Ordnance Office. So from the beginning of computers, we've wanted to do floating point math. So that brings up this idea of how do we store numbers? So if we use something like fixed point, we notice that we get this very, very low precision. We don't have a lot of flexibility. And so we use something called floating point, which is basically, if you've seen scientific notation before, you see that we can represent, it does a very good job at, so it's normalized, of course, so there is never a leading 1. I wish for some reason, I think the file is too big, so it doesn't like my annotations anymore. And this is free software, so I'm pressing down right now, and it's not doing any highlighting. I'm ready to create accurate artillery systems. Nice. Hey, we can look at some of those calculations too sometime if we do some math. So basically, in the same way that we do normal scientific notation, we can do that in something called floating point, which follows the IEEE 754 standard. And so basically this means is that we will have always a 1, because if we remember from regular scientific notation, we always have a leading 1. And we actually do something very clever here. So we can actually save on storing this bit of 1 in a register, because we know it's always going to be 1 in scientific notation. So we can actually get away, and we can only store these bits over here, and we'll call these the mantissa. So this will be the mantissa. And then we'll take some amount of bits, and we'll use this to store an exponent. Now we should watch this video by this professor at National University of Singapore, or National Singapore University, and he actually has an alternative to IEEE 754 floating point standard. So like we said, we're going to be storing a fractional part and an exponent part in binary. So instead of having this number system that works well, that's we can do addition with, we're now making a number system that can store the maximum amount of values in the highest precision values. And so that's when we get this IEEE 754 floating point standard. So basically how it works is that this most significant bit is our sign bit. Followed by our sign bit, we have an exponent bit. And this exponent is actually has an offset. And then after this exponent bit, we have our fractional bit. And this fractional bit is something called a mantissa. So this will be like the decimal portion. This is our exponent portion, and this says if it's positive or negative. Now, if you think about why it's ordered in this way and why we don't have exponent at the end, or why don't we have sign in the middle, the reason is, think about if we were to do a comparator. Think about if we were to compare two numbers that are floating point. So how would we determine if one is bigger than the other? Well, the very easy way, if we have this format, is first we compare the first bits. Now, if the sign is different, the one with the positive sign is going to be, of course, the bigger number. But then we have exponent next. So we can just compare the exponents. So the larger exponent will, of course, be the larger number if the signs are the same. If the exponents are exactly the same, then the one with the larger fractional portion will be the larger number. So that's why it's laid out in this fashion. Okay. So in IEEE 754 floating point standard, there's some special combinations for these. So how we can actually represent numbers like infinity. We can represent numbers, so both positive and negative infinity. We can represent not a number. So if we get some result that doesn't make sense, if we do something maybe, if we do something that's illegal, we can get not a number, and we'll see that that actually can take up a lot of space, and we don't actually like that. But we see that we can represent some other things. So 0 has a special representation, negative infinity has a special representation. If I'm not mistaken, negative infinity will be a negative in the sign bit. The exponents will all be 1, and then I think the fractions are all, they're all zeros or they're all 1s. So let's look up a IEEE 754 floating point standard. Let's look this up. Okay. So they've got rounding rules, recommendations, character representation. Okay, recommended operations, rounding. Okay. Basic interchange format. Okay. Oh, well, this is actually terrible. They don't even tell you what these special representations are. Nice. Okay. We can go ahead and move on then if they're not going to give us something interesting. Now, there's something else called double precision. Basically what they do there is they extend this from 32 bits to 64 bits. They add some more space for exponents, and they add some more space for the fractional portions. Really simple, very easy concept. Okay, so let's talk about exceptions and interrupts for a second. So what should happen on an overflow or underflow? So let's look at underflow for a second in case we were unsure on that. We're unsure on what that is. So floating point offers a new kind of exceptional event as well. Just as programmers want to know when they have calculated a number that is too large to be represented, they will want to know if the non-zero fraction they are calculating has become so small that it cannot be represented. So say we want to represent, 1 over 1 googolplex. Okay, we probably can't represent that in 32 bits. So what happens is that's very, very, very close to 0. So that ends up being something that we call underflow. So let's move on to exceptions and interrupts again. So what should happen on overflow or underflow? We want the computer to know these are a special event because we want to know, hey, something went wrong. Don't necessarily treat this like a correct answer. So the computer has to know this. So some computers signal these events by raising an exception, sometimes called an interrupt. So this can be a very confusing thing. Exceptions and interrupts. Sometimes they're given different meanings, and so these two things can sometimes not equal the same concept. So an exception or interrupt is essentially an unscheduled procedure call. So this is mainly for something like corrective action or notification. The address of the instruction that overflowed is saved in a register, and the computer jumps to a predefined address to invoke the appropriate routine. So basically what we can think of happening here is a problem happens. So let's give an example. So let's say you catch somebody breaking the law, right? So what you're going to do is you're going to pick up the phone. So picking up the phone is raising an exception or raising an interrupt, and you're going to call the police. Now you call the police come down, and they're going to go through the process of collecting evidence and doing what they need to do. So that's this appropriate routine that we're talking about here for the exception. So the interrupted address is saved, so this is the collecting evidence, so that in some situations the programs can continue after corrective code is executed. So section 4.9 covers this in more detail. This isn't very important once you start getting into errors in the control section of the pipeline, because control, say if the outcome of some arithmetic operation determines a branch, well, we're going to need an interrupt or something to happen so that we don't mistakenly branch to a different location. We don't want to exit a loop before we're supposed to. So RISC-V computers, so this is a RISC-V specific architecture feature, do not raise an exception on overflow or underflow. Instead, software can read the floating point control and status register to check whether this has occurred. So basically what they're saying here is they're not going to fix the problem for you, but they're going to allow you to check if there was a problem. Does that make sense? Does everyone get the idea of exceptions and interrupts? Let me get some of this delicious protein powder. Listen, this would be my greatest life goal. 0.1 plus 0.2 is not equal to 0.3. I'm calling the IEEE police. Good. Call them. I'm gonna raise an exception to IEEE just for that. Okay. Okay, so the dream. The dream, we get a sponsorship by Beachbody. That way I can get free Shakeology instead of having to pay $130 a month for a bag. That's the new dream of the stream. That's it. The only money that I would ever want to make is getting a Shakeology subscription where I can get free protein powder. Because this stuff is expensive. But I use this as like a meal replacement. Stuff's good. It's got flax seeds in it. It's like I'm drinking sand. Doesn't that sound appealing? Don't you guys love that? Don't you guys want to drink sand? Okay, here we go. So here's how we represent numbers that are special cases. So not a number can be, we're going to have an exponent that's maxed out, 255. The fractional portion can be anything, we don't care. Or in double precision, it can be 2047, which is the maximum for the double precision one. And then the fractional part can be non-zero. So we see that we can actually represent a lot of not a number. So if we go back here and we look at, we see that we have 52 bits in double precision for a fractional portion. And we see that any case where the fractional portion is non-zero and the exponent is 2047, we see that we actually have in double precision 2 to the 52 minus 1, or no, 2 to the 52, yeah, 2 to the 52 minus 2 cases where we get not a number. That seems like a lot of wasted space, doesn't it? That seems really, really bad. Am I wrong? That seems like we're wasting so much space and we're wasting so many combinations to represent not a number. Okay, let's move on. Let's move on from this garbage. Okay, and here they're showing you what infinity looks like, correct? So infinity here is going to be all ones in the exponent, zeros in the fraction. So all ones in the exponent bits, zeros in the fractional bits. And so 0 is just going to be all zeros, of course. Okay, so we'll probably do a lecture sometime about why IEEE 754 standard is bad. I need to read the paper by, I think his name is John Gustafson. He has an alternative to this that's a lot better. I think it's called like enum, maybe? Something like that. Okay. So we can skip the rest of IEEE 754. A lot of this is just examples of how to do this conversion. If you want, just look up the IEEE 754 standard online. However, from an architect's point of view, this is interesting knowledge, or it's foundational knowledge, but not necessary to know for the majority of cases. We're not going to be hand converting a bunch of decimal numbers into IEEE 754 standard. I would very much not like to do that. Maybe in a problem-solving stream we'll do that. Okay. So let's see. So following IEEE guidelines, the IEEE 754 committee was reformed 20 years later after the standard to see what changes, if any, should be made. The revised standard, IEEE 754-2008, includes nearly all the IEEE 1985 and adds a 16-bit format for half precision and a 128-bit format for quadruple precision. I can't even imagine how bad of a system quadruple precision is. If we already have 2 to the 52 minus 1 combinations for not a number in double precision, Or what are we going to have? 2 to the 104 combinations of not a number? That seems terrible. Please someone tell me that I'm wrong. Am I wrong? Say it ain't so. Okay. Let's move on. So we're going to see in addition that you basically just have to convert these to decimal by hand and then do some addition on them. And I don't think they show it in here, but if we were to construct the circuit to do addition or subtraction or multiplication or division of floating point numbers directly, it's incredibly complicated because, as we can see, it's not based on a real number system. It's based upon a made-up number system that doesn't mathematically make sense. It's a format that you have to decode into a form that makes sense. So it's not great. Okay. Let's see. Let's get to an interesting section. Okay, so you guys remember the very simple addition and subtraction circuits and the multiplication and division circuits. Now, if we wanted to do floating point arithmetic, we need this kind of monstrosity. So we need to take our two 32-bit we need to take our two 32-bit floating point numbers. The first thing we need to do is we need to take our exponents out, and those are going to be selected based upon some control signal, and we're going to increment them or decrement them. We have to have specialized rounding hardware down here. Basically what we have to do is we have to decode these two, use some very large ALU to do some computation, do any shifting, and then we need to re-encode it into the specific form of IEEE 754 floating point standard. So we see that this is some nasty hardware. This is not necessary unless you're going to the field of computer arithmetic. You don't. It's good if you can trace through this, but not necessary. Floating point multiplication works in a very similar fashion of decoding and re-encoding. So we can skip over most of this, and we'll see that the RISC-V instruction set supports a lot of these same types of instructions. So they have floating point addition for single precision, floating point subtraction, single precision, and double precision. They have division, square root even, so they have dedicated hardware to do square roots, or at least they can simulate square roots. Okay. And so here's all our floating point operations that are defined in the RISC instruction set. So like I said, adds, multiply, divides, square roots, and then double precision of those operations. There's equality checkers. There are less than equals for single precision and double precision. And then there's loading a floating point word or storing floating point words, being the single or double precision. Okay, any questions so far? Any of this stuff? So we see that the RISC instruction set has a lot of different operations that we can use. Now, something that an x86 instruction set, so something like an Intel processor would have, is they would have the ability to take values from memory directly and do operations on them. It's also very likely that they would have the ability to do maybe quadruple word operations. Well, the x86 instruction set it's nasty. It's a very nasty instruction set. You can do a lot of things with it, but it's very nasty. Okay, so let's look at this hardware-software interface key point. So one issue that architects face in supporting floating point arithmetic is whether to select the same registers used by the integer instructions or to add a special set of floating point registers. So this is whether or not we want to have a split register file. So because programs normally perform integer operations and floating point operations on different data, separating the registers will only slightly increase the number of instructions needed to execute a program. So this basically says that most of the time when we're working on floating point numbers, a lot of times we're going to be working on mixes of floating point numbers. And when we're doing lots of integer calculations, it's mainly integers and integers. So it makes sense in a lot of cases to keep these separate. The benefits of separate floating point registers are having twice as many registers without using up more bits in the instruction format, having twice the register bandwidth by having separate integer and floating point register sets. So by twice the register bandwidth, this means that now instead of having to go through the same part of the register file to get the integer registers, we can go someplace else and we can get the we can go to the floating point registers. So that's what we mean by this bandwidth. Okay. So here they have so this is just a C program, like a function and a C program that uses a float, or has a float output and a float input. So they do this floating point division. Oh, it's just a conversion from Fahrenheit to Celsius, of course. And then they get this as a output. So this is a floating point word F0, and so they load in a floating point number into that register, F0. They load in the other floating point number into the other register. They do a single precision floating point division to get this 5/9. That's what this is calculating. They load in another floating point word into F1, which is 32 degrees Fahrenheit. They do a subtraction where they subtract F10, which was the argument. The argument of the function is in F10. So they subtract 32 from F10, and they store it back in F10. Right there. And then they do the multiplication of 9/5. 9/5 or 5/9? 5/9. Of 5/9 times that answer right here. And then they return from the function. So they use, like we talked about in the previous lecture, they do a jump and link register x0, and they go to some predefined return point. So pretty simple. I think we can understand that. They go over another complicated loop, but we can go ahead and skip over that. So elaboration. So C and many other programming languages use the array layout discussed in the example called row major layout. Fortran instead uses column major, whereby the array is stored column by column. Okay. Another elaboration. So another reason for separate integer and floating point registers, so this is the idea of that split register file like we were talking about earlier, is that microprocessors in the 1980s didn't have enough transistors to put the floating point unit on the same chip as the integer unit. So many of you might have heard about the idea of coprocessors. So that's exactly what they're talking about here, coprocessor chips. So now a lot of times we refer to a GPU as a coprocessor. But back in the day, something as simple today as floating point was considered worthy of a coprocessor. In fact, in many ways, you could consider something like the TPU, the Tensor Processing Unit, Google's machine learning accelerator, to be a coprocessor. All the Tensor Processing Unit basically does is lots of matrix multiplications. In fact, let's look up the Tensor Processing Unit diagram. I saw this in a research paper. I'm pretty sure I can find the block diagram. Here it is. Let me view image and let me open this up on stream. Okay, so here we have the tensor processing unit. So here's just the interface to whatever it's connected to. There's a host interface, so the PCIe, and then we're going to the actual CPU here. We have control kind of centered around. We see that they made the unfortunate decision of going with DDR3 DRAM chips instead of using something like high bandwidth memory. So something like HBM. So the first generation tensor processing units, they actually had fairly modest performance improvements over GPUs, namely because GPUs moved very quickly into using high bandwidth memory, while the tensor processing units, they weren't as forward thinking and they used DDR3. Now we see though, so they have this systolic array data set up, and then they have this unified buffer for local activation storage. This isn't to scale, by the way, this picture. However, this matrix multiply unit, this is the entire processor. This entire processor is a giant matrix multiply unit that has accumulators, which is basically just addition, and then they have their activation and normalization down here, which are separate mathematical operations. So this uses the activation functions. A lot of times I think so I think RETLU is what it's called, and sigmoid is another activation function, and then just normalization. But we'll see look at this high bandwidth though, 167 gigabytes a second. This is why the tensor processing unit enables machine learning. 167 gigabytes per second, and then back from the normalization step, another 167 gigabytes per second wide lane. Incredible, absolutely incredible. But if we look at the tensor processing unit, we see that DDR3 is not that complicated. DRAM is basically just a bunch of transistors and capacitors. An interface, fairly simple. PCIe, that's just a protocol. We have an instruction buffer right here. This is just a buffer. We have all this control centered around here. These are just very simple combinations of gates that, based upon the instructions, they just turn different lines on and off. Nothing special. Accumulators, this is just addition. Activation and normalization, these are just some other arithmetic functions. Await FIFO fetcher. Oh, yeah, the weight fetcher. This just fetches weights in a FIFO queue from DRAM. And then basically the only novel part of this is they have this systolic array data set up, and then just some giant matrix multiply unit. So there's nothing special about the TPU, the tensor processing unit. It's a very simple device. However, machine learning is all linear algebra. And so that's a kind of coprocessor. That's one kind of coprocessor that's out there. Now, if there's someone out there that's clever enough, you may have noticed that the background of the stream, you might have noticed that this screen, this is actually the die of a GPU. This is the die of a Fermi architecture NVIDIA GPU. I googled I just googled the die, and I changed the coloring a little bit. So that's actually just a GPU. Okay, let's move on. Listen, guys, if you're enjoying the stream, make sure you guys tune in Monday through Friday and Saturday, Sunday. I've got the schedule down below. Give me a follow if you enjoy the content. We'll learn a lot of stuff together. And everything from engineering topics all the way through languages. Languages being German and Japanese. We're going for German and Japanese on Saturdays. All right. So let's talk about accurate arithmetic for a little bit. So unlike integers, which can represent exactly every number between the smallest and largest, we don't have that luxury with floating point numbers. So oftentimes we need to do rounding, and so IEEE 754 has lots of modes for rounding. So IEEE 754 has 2 extra bits on the right during intervening additions called guard and round respectively. So guard is the first of the 2 extra bits on the right during intermediate calculations of floating point numbers used to improve rounding accuracy. Oh, I'm sorry guys, that is the wrong screen. My bad. Listen, this is amateur hour. Amateur hour. Okay, so this is guard. Don't worry, you just missed some text. We'll be okay. We can make it. Okay, so round. What's round? Okay, we know what rounding is. Never mind. So rounding with guard digits. Okay. So what you can think about with rounding is with the final digits, it's basically just a test of whether or not, say if round is 0 or round is 1, that'll just determine whether or not it rounds up or rounds down. If that round bit is 1, it will round up that last bit. If it's a 0, it'll round down. And a lot of times they actually have 3 additional bits at the end to determine exactly which kind of rounding. So that's this idea of sticky bits. So it's a bit used in rounding in addition to guard the round that is set whenever there are non-zero bits to the right of the round bit. So like I said, in IEEE 754 standard, they actually use 3 bits for rounding. Okay. So what is RISC-V and MIPS and PowerPC and SPARC and AMD and Intel AVX architectures? They provide a single instruction that does multiply and add on 3 registers. So a lot of times this is called fused multiply add, and that's exactly what they call it down here. So the reason why processors generally have this operation is because just like we saw in that tensor processing unit architecture, what did we have in that tensor processing unit architecture? We had a giant matrix multiplication unit, okay, followed by an accumulation stage. Now, listen, I'm going to need someone to help me answer this. If we have a giant matrix multiplication unit, and then we do addition immediately afterwards, what does that remind you of? What kind of instruction? Could it possibly be a fused multiply add? Could that be the backbone of machine learning? The answer is yes. The answer is yes. In NVIDIA GPUs, the instruction is called FFMA. It's floating point fuse multiply add. And that's in the NVIDIA instruction set. So we see it's everywhere. It's in all of these CPU architectures. It's also in accelerator architectures. Yep, and that's just fuse multiply add. So the big picture that follows reinforces the stored program concept from chapter 2. So what's the big picture here? Bit patterns have no inherent meaning. So if we have 32 bits, what does that mean? It means whatever we tell it to mean. Is it a signed number? Is it an unsigned number? Is it IEEE 754 standard? That's for us to decide. So we have to decide the architecture that tells the user what it is. So they represent signed and all these things that we talked about. The major difference between computer numbers and numbers in the real world is that computer numbers have a limited size. So we can't have an arbitrarily long number in a computer. They have to fit into our registers. They have to fit into memory. So most of the time we pick a multiple of 2. We pick a multiple of 2 because a transistor can have either an on or off position. So that is 2. So that means we inherently have to use base 2. The most common numbers that we use for arithmetic operations are 32 bits, and 64 bits. If we're doing something reduced precision, namely machine learning stuff, sometimes we even have 16 bits, or what's most common nowadays in a lot of inference tasks in machine learning is int 8s, so 8-bit integers. Because think about it, if we have an 8-bit integer and we want to do some operation, if our register size is 32 bits, we can store 4 int 8s in the same space that we can store one normal int. Isn't that fun? Isn't that grand? Okay. So let's see. Okay. This is some elaboration. So let's look at this elaboration section. So to accommodate comparisons that may include not a number, the standard includes ordered and unordered options for compares. RISC-V does not provide instructions for unordered comparisons, but a careful sequence of ordered comparisons has the same effect. So apparently Java doesn't support unordered compares either. Okay. So then they go a little bit more into denormalized numbers or subnormal numbers. That's okay. So subnormal numbers, as we know normalized means that we have a 1 up in front. However, we can also easily tell that if we want a subnormal number, it's a 0 up in front, but that's if we really, really want to push the limits of our precision. Okay, so let's talk about parallelism for a second. So parallelism is where we get most of our performance. So let's see what they have to say. Many graphic systems originally used 8 bits to represent each of the 3 primary colors, plus 8 bits for the location of the pixel. The addition of speakers and microphones for teleconferencing and video games suggests support of sound as well. So audio samples need more than 8 bits of precision, but 16 bits is sufficient. Every microprocessor has special support so that bytes and half words take up less space when stored in memory. And so 2.9 had a little bit on that. But due to the infrequency of arithmetic operations on these data sizes in typical integer programs, there was little support beyond data transfers. Architects recognized that many graphics and audio applications would perform the same operations on vectors of these data. So that means we're going to have basically 2 giant vectors that are all going to be doing the same, similar or exactly the same operation. So if you think if we want to turn an image to grayscale, so in order to turn every pixel the correct shade of gray, that is not going to be dependent on the surrounding pixels. We can do that so that we change every single pixel independently. That means if we had, say, 20 ALUs, we could make 20 pixels gray at the same time. And so that's this idea of parallelism. So given that parallelism occurs within a wide word, the extensions are classified as subword parallelism. So that means we're packing these smaller sizes, so 8-bit, 16-bit, or 32-bit, into a larger size. And so that's what I mean by subword. So a word is 32 bits, so we can fit 4 8-bit pieces of data into a word. We can fit 2 16-bit pieces of data into a word. And so this is what we call data level parallelism. That means we have data that's small enough that we can pack it in a certain way that we can do something on it. And so what we usually call this is SIMD, or single instruction multiple data. So if, say, we were doing some kind of addition or subtraction, and we just packed everything together into, say, a single string of data, we shoved it through some arithmetic unit and it came out the other side, then we did a single instruction, but it worked on multiple pieces of data. Does that make sense? Okay, so let's move on. So let's look at x86 hardware. Let's see what we have in actual Intel chips. So the original MMX multimedia extension for the x86 included short vectors of instructions to operate on short vectors. So SSE, streaming SIMD extension. So like we said, single instruction, multiple data. This was added later, okay. So Chapter 2 notes that 2001 Intel added 144 instructions to its architecture. Oh my goodness. Listen, remember when I said x86 was really confusing and a mess? I'm pretty sure 144 instructions is more instructions than the entire RISC-V architecture. And this was added in 2001. This wasn't the entire instruction set is 144 instructions. They added an additional 144 instructions to the instruction set. Let's actually look that up. How many instructions in x86? x86 instruction listing. Okay. How many do we have? Let's look at Pentiums? Are they going to give us modern? Let's just look at Pentium then, I guess. Added with Pentium 2. Oh, x86 64. Okay. 8087 instructions. As we can see, there are a lot of instructions that have been added to the x86 instruction set over time. This is why nobody likes to program in x86. It's a mess. And also, look at these instructions. Look how messy these look. RISC instructions look so clean and pretty. These look... Oh my goodness. I couldn't imagine trying to program in x86. I don't ever want to imagine. Okay, so let's move on a little faster. I think this is our last section. Going faster, subword parallelism and matrix multiply. To demonstrate the performance impact of subword parallelism, we'll run the same code on the Intel Core i7, first with AVX, then with it. Okay. So here we have the unoptimized C version of double precision matrix multiply. So we just have nested for loops. We use doubles, and then we iterate over the entire matrix and do this multiplication at the very end using the indexing from these two for loops. Okay, makes sense. So where's my graph of performance? Okay, so here's what it turns out to. So we have a vector move instruction, another vector move instruction, a vector multiply, I think, a vector add, and another vector move. So this is probably moving it into its final location. The compiler uses AVX versions of the instructions instead of SSE2, presumably so it can use 3 addresses per instruction instead of 2. And here we have the optimized version of the code. And you see we have a tighter loop in here. We have a fewer instructions. We see that we're still using the same vmove operations, the vmultiply, the vadd, and the vmove again. Slightly different. I'm not entirely sure what these instructions are actually doing. So here we have a jump to exit out of the loop, I'm guessing. So vBroadcast SD. That's interesting. So let's see if they tell us what vBroadcast does. Here we go. One solution is to place 4 identical copies of the 64-bit element B side by side into the 256 YMM register. So that's what broadcast does. Broadcast basically says, okay, here's a single piece of data. I want you to give this to many people or many locations. And so apparently this performs The AVX version is 3.85 times as fast. So it's close to a factor of 4 increase that you might hope for from performing 4 times as many operations at a time using subword parallelism. So this is that great idea of subword parallelism that we wanted. Okay. Let's continue on. Let's go over the fallacies and pitfalls, and then we have some free time. So fallacy 1. Just as shift left instructions can replace integer multiply by a power of 2, a shift right is the same thing as an integer division by power of 2. So this is a fallacy. We have to remember that this doesn't take into account sign. So we have to look back at how we do 2's complement in our weighting scheme when we do this. So we can't just shift to the right by 2 to divide, but we can shift to the left in order to multiply. That's a very, very convenient thing we can do. So pitfall, floating point addition is not associative. So associativity holds for a sequence of 2's complement integer additions, even if the computation overflows, because they're approximations of real numbers, and the computer arithmetic has limited precision. It does not hold for floating point numbers. Okay, another fallacy. Parallel execution strategies that work for integer data types also work for floating point data types. So just because we can parallelize a lot of integer operations doesn't mean that the same is true for floating point. As we saw earlier, floating point numbers are structured very differently from integer operations. Another fallacy. Only theoretical mathematicians care about floating point accuracy. Well, that's not true. If you wanted, if you're a physicist, you probably care about it. If you do many operations on spreadsheets, and say you're in the finance sector, having a single instruction failure could be very, very bad for you. Okay. This is talking about the SRT division error. This was a very famous thing. Intel lost billions of dollars because they did division wrong. Okay, so here's the secret story. So what basically happened was Intel forgot to fill in some entries on a lookup table for their SRT division algorithm. Now, because they did that, it would cause errors when you would do floating point division. So what ended up happening was, at first they denied the problem. After they realized they couldn't deny the problem, they said, okay, we have a problem, but nobody will experience it. Barely anybody will experience it. Only super users that are doing millions upon millions of division calculations may experience this. And then they said, okay, some people experience it. Maybe if you give us your chip, we'll do a replacement. And then finally they said, okay, we have to even stop shipping Pentium PCs. And we have to do replacements for every single Pentium part out there because they're all subject to this bug. And so I actually have a keychain that has a old Pentium SRT division error flaw on it for these buggy chips. Very funny, very funny. Okay, so that basically concludes us for computer arithmetic. Now, hitting live, are you still here? If you're still here, we can look over some Verilog code for arithmetic units. Okay, let's look up some stuff. Let me open up this browser instead. So, Verilog. Hello, how's it going? Okay, So what do we want to look at? Do you want to look at multiplication or addition, or just show something basic? Okay, so let's look up Verilog carry ripple adder. This is the most basic adder that we can make. This one will probably be fine. And then I'll get some software where we can actually show this some other time. Oh, this is VHDL. This is Verilog. Nope, this is still VHDL. It's the test bench, Verilog implementation. Okay. So in Verilog, it's very similar to C in a lot of ways. So what we first do is, so here they're building a carry ripple adder, a 2-bit carry ripple adder is I think what they're doing. Let's see. Yeah, 2-bit carry ripple adder. So in Verilog, you start everything out with a module, and so oops, wow. You start everything out with module, and then just the name, and then you define your port list, and so you do input 1 to 0 because you have to remember that your most significant bit is farthest on the left, so it's generally done this way. So you do your inputs and your outputs in no particular order, and so these are going to actually physically connect wires. Okay. Sure. So these are our inputs and outputs of the actual chip itself. The wires, what we specify with wires are, they are things that they don't touch the outside world, and so we're not going to put them in a port list because they're not inputs or outputs to the system. They're just things that we need in order to connect internal components together. So then what we end up doing here is we know that if you were here for, I don't think you were here for one of the computer architecture streams, but basically the input to a, let me open up another. It would be very convenient for me to have these things open side by side. Okay. So let's do some drawing. I actually did a lot of digital design work, so. View. Let's see. Page. Style. There it is. Plain. Okay. So basically, we have our inputs and outputs, and so these are all going to be defined in our port list. So we'll just write in, out, and then maybe in, oh, or out, because I start with an O. Then on the inside, these are going to be wires. And so wires just say, we need these to connect internal components, but they're never going to touch the outside world. So then, are you familiar with why we need to have a 0 carry-in? It basically comes from the fact of when we're doing addition. So if we're doing something like 0, 1, 1 plus 0, 1, 1. So the way we design a basic adder is out of these blocks we call full adders. And so full adders have 3 ports. They have a B, carry in. And so if we're going to use this basic design, A, B, carry in, the first one, to calculate the first bit, we'll just go ahead and tie that to 0, right? Because this is our first bit. There's no previous stages, so we know we won't have a carry. And so here we'll have our C out, which we will connect to the C in of the next circuit. This will be our sum 1, this will be sum 0, and then we will have a carry out here. So we'll call this carry out 0, carry out 1, A1, B1, Cn1, A0, B0, Cn0. So this is the basic design that we're going for in this circuit. This is VHDL. So what we basically do is we define wires for our carries and wires for our sums, because that's internal to this big circuit. So we can think of here's our module that is ripple, carry, adder, to FA. So this big box right here. Now, when we say we have an input 1 to 0, so that means we have two inputs for term 1 and two inputs for term 2. That means that A and B are going to be coming from out here, and then these A and B are going to be coming from down here. So this is A and B 0 and A and B 1. So this will be I add, we'll just do I add 0 and I add 1. And remember, this is an array, so there's 2 in here. Now, the first thing we do is we do an assign, or so let's take a step back actually. Let's take a step back. So let's disconnect everything. Let's actually even get rid of the full adders. So we named wires. So we have wires in here, correct? But we don't know where they go yet. We haven't connected two things together, but we've named wires. So we basically have 2 to 0, so 3 wires, and 2 to 0, 2 wires. And then we also know that the first carry wire is going to be assigned, we know that the first carry wire is going to get a single bit, so we know that it's a single bit of 0, always. It's a constant 0. So here, we're assuming that we've already made a module for a full adder that has an argument for a single bit term 1, or a single bit of 1, a single bit of 2, a carry bit coming in, an output sum, and an output carry. So all of these dots right here, these are, so you can either put in arguments positionally, which I'm sure you know. I believe you said you had a computer science degree. So this just makes it so you don't have to put in arguments positionally. So we can go ahead and define this as, we have I bit 1 here, and then that's going to be coming directly from this I add term 1, both of these. Let's see, I add term 2, 1. Okay, so that's actually not. So this is 1 and this is 2. So this is actually slightly confusing because that means this is A0 and A1, and this is B0 and B1. Okay. So I add term 1 is A0 and A1. I add term 2 is B0 and B1. So this is an array of A's and an array of B's. So basically what happens here is we put the first bit, which is I bit 1 from term 1, into this first full adder, and it's coming from the outside. And we take the first bit from B0, from I add 2. Then we have a carry in, which is W carry, but we define W carry to be a constant of 0 right here. So in the actual circuit, so I'll just nickname this full adder 0. In the actual circuit, this Cn is just going to be pulled to ground. if you were to look at the actual circuit. So this just, it's grounded out here, so this is always 0 volts. And then we have a carry out right here, W carry. This is a wire, so this is going to be internal. This isn't going to touch the outside. However, this out sum right here, okay, that is going to a wire. Okay. So this is going to be our out sum. So we'll call this O sum, and this will be O carry. So then we have another full adder. We're going to connect it similarly with the other inputs here. We see that with the input carry, we see that these are both given the same name, W carry 1 and W carry 1. That means physically these are connected. So so out carry here is the same thing as in carry. We see that sum is also just this wire. It's the other index. We see that we have an output as well, another carry here, a wire that's right here. Now we have this final assign statement, correct? So in this final assign statement, it says our output result, which is this output here. So we basically have 3 spots for output because we have this vector of 3, this O result. It says that the upper 2 bits are going to be, or the upper single bit will be W carry of 2. So that's going to be our output from our second full adder. So that's going to be this bit right here. And so we can even label that W carry. Now, the next part of it says, okay, the bottom 2 bits are going to be W sum. So this vector of wires right here that we assign to the output of both full adder sums, so this is also O sum, it's going to be these 2. So when we synthesize something like this, most of the time it's just going to give us some predefined ALU that's on the chip, but this is basically how we would do this. This is like a basic full adder. So it's all modules and instantiations. So this is an include. So this is how they design. So what is this? Okay, so they're parametrizing this. That can be a little bit confusing. We can go over that some other time. Let's go over another example. So let's look at something more interesting. So this is getting really down into the nitty-gritty of something like Verilog. Yep, you followed that? Okay, good. So what's important to know is that there's 3 levels of there are 3 levels of design. There is 1, there is gate level. 2, there is, oh, what's the second one? Is it functional? There is functional design, I think. And then 3, there is behavioral design. Now, gate level design is exactly what it sounds like. So if you were to take something like this, if we go back and we design a full adder again, and so if we say a full adder is, okay, so when do we get a sum? We get a sum if there's an odd number of inputs. So if we do A XORed with B XORed with Cn is our sum, And then our carry, or let's see, our carry out for a full adder will be if we have A XORed with B. So if we have an odd number of this and Cn, or we have A and B, I'll just put a dot here instead. This is our C out. So when we're doing gate level modeling, we would specifically specify the gates we need. So for something like this, let's see what would be the best way, how to construct this. So let's consider 2 input gates. So we would do something like, I think this is legal syntax in Verilog. If you had already defined a port list of what your inputs were, I think you can go XOR, comma, or parentheses, and then it will be A, comma, B, comma, let's say 01. Let's say this is, or sorry, my bad. The output comes first. So let's say 01 A, B. So this says we're going to XOR A and B, and the output 01 will be that result. So then I would do XOR 02, comma, 01, comma, Cn. So this would give me this result XORed with Cn. So we've done our sum so far. So we can actually just call this sum instead to be a little more clear. So then let's do this bottom part for C out. So in this bottom one, we already have this calculated. So all we would need to do is AND. We can call this 02 because we need a new variable. This will be ANDing 01, this XOR, which we already calculated here. Let me make this more clear so it doesn't look like a comma. 01 and Cn. Or A and B. So let's go ahead and do A and B since we're already doing AND. So let's do AND 03 A B. And then let's generate our carry out. So this will be an or C out, comma, we want this first term, which is 02, and then we want this AND term, which is 03. So this is how we would do gate level modeling in Verilog. So assuming that we already had our input specified, we defined 01, 02, and 3 to be wires because those are internal to this device. Because you see that our only outputs to a full adder are carry out and sum. Then we would have an output. We'd have an outputs in our port list of only C out and sum. Okay, makes sense. So functional design gets a little bit clearer. It's a little bit easier, but you have less control. So let's do, is it view? No, it's tools. Oh, I'm not clicked on it. Whoops. Page. New page after. Okay. So let's look at functional. So functional is even easier. So functional says, you can basically think of this as Boolean algebra. So in this one, I could simply say my C out, or here we would put assign That's a keyword here. We would be assign cout equals what's the let's do sum first. Let's do assign sum equals a XORed with, well, what's the XOR symbol? I think that's what it is in Verilog. I think this is the XOR symbol. So it'd be A XORed with B XORed with Cin, and then we would do assign cout equals A XORed with B ANDed with I can never draw an ampersand. Instead of an ampersand, I'm going to do this. ANDed with Cin, or, which is the same pipe, or A and B. So we can literally just write, and so there's supposed to be commas, or what is it? Semicolons at the end. So yeah, you can just do the Boolean algebra for functional. Now the last one, which is the easiest one, is behavioral. Now I'm sure you can guess what this is. So behavioral, S, so what you would do is you would specify a 3-bit. So let me think about how you would do behavioral for a second. So it's 2 bits. So I want an output. I know the output's going to be 2 bits. So I would have, let's go to the port list because we need the port list to understand this better. So it would be input sum. It would be input Cin. It would be output. Oh, sorry. Input. Sorry, I don't know why I said that. It's input A, comma B. Input, and then also we can just put in the same line, Cin. Now outputs. Now remember, this is a port list. Output sum cout. So the way that we would do this, if we wanted to do behavioral, we could just do assign cout, comma sum is equal to A plus B plus Cin. So we can actually just use addition here. And so what this does is it takes this result and it stores it in these 2 bits. Remember, if we don't assign an array right here, it's just a single bit. So you can think of this as 3-bit addition. So we can just test this out and the synthesis to the same thing, and the synthesize to the same thing. That depends. So when you have something like this is where the design trade-offs come. So if you're at the level of design of gate level, you will absolutely get these gates if you specify them. If you're at functional level, well, you're telling it the Boolean equations, but maybe it can find a slightly more clever way to do this. And then when you're doing something like this, where you're literally just giving it plus symbols and you're assigning it to an output, it has free range. It will try to do as best as it can, but this is actually one of the biggest problems in circuit design today. Circuit design has such a high overhead because it's not actually possible to get an optimal design using behavioral synthesis a lot of the time. It's been an open problem for 10 years, 20 years or so since behavioral design really came out. So some of the times with behavioral, so here's my intuition, just going what it will do if you do this on an FPGA. So Henning, here's my question. What is your concern with like VHDL or hardware description languages? Are you interested in FPGA type stuff or all the way to the fabrication of a circuit? Because the outputs can be very, very different. Because if you're concerned with the fabrication, the synthesis is completely up to you. There are libraries that have pre-built components like adders and multipliers. However, okay, yes, I want to make a toy CPU on an FPGA. Okay, so here is how that works on an FPGA. So you do this when you, so if you use some, do you have a specific platform you're working on, like a Xilinx or an Altera board? I worked on Xilinx boards, so I'll just go with that. So I used Vivado. So what Vivado has is it has a manifest of every component on an FPGA. So what happens is when you give it a design like this, like an addition, so what a lot of people think is that when you get this FPGA, so we'll call this a Spartan 5 FPGA. That's a common one from Xilinx. So on a Spartan 5, they may have a dedicated section of this chip that is an addition unit, which is likely, or very likely a multiplier. So when you do something like, okay, I want to do 32-bit multiplication, and you have two 32-bit inputs, and you do A times B equals P, like the product. The other way around, of course. So P equals this. A lot of times, once you get through synthesis, so you can pull up, what will happen is it will pull up the synthesized design of the resources that it used on the board, and a lot of the times it will simply show you that it chose to route all your connections of your inputs to this multiplier. Does that make sense? So it doesn't, so all these boards or anything, a lot of times what people think they are is just a sea of gates. That's a very naive and old design. It used to just be, it was an infinite amount of gate, not an infinite, but it was a lot of gates that it would connect as needed. That's not really the case anymore. Okay, makes sense. Yeah, so what you're talking about, making like a toy CPU on an FPGA, yeah, I've done that before. It's a lot of fun. We can always dedicate some time, maybe a little bit, maybe 30 minutes to 45 minutes per week, going over some Verilog type stuff. It's there's a couple little subtleties in the language that can be a little confusing, especially when you. So all we've talked about so far are combinational designs. These are designs without a clock. But what you're talking about, Henning, is a sequential design, which I'm sure you know since you have a degree in computer science. But yeah, so these designs right now, so this wouldn't really work that well in a This doesn't work incredibly well in a sequential design because it's not synchronized with any clock. So that's dangerous because you're not going to be certain that your addition is complete at the end of a clock cycle or when you think that you may need it. Okay. So anything else we want to go over? It's 9:35. I've dedicated another 25 minutes to this stream. What else do we want to do? Do we want to do anything else? What else can we go over today that'll be interesting? Oh yeah, of course, Henning. Anytime. Like I said, if you're interested in the content, I've got my stream schedule below, and we can go over if I run out of time, or not run out of time. If I have extra time, we can always do fun things that people suggest. Okay, let's see. Is there anything else interesting? So then there's also things like test benches. Test benches are ways of testing your design and ensuring correct functionality. Okay, so let's look at what we're going to be doing tomorrow. Talia, engineering today, I want to learn why you aren't changing your name back to Why So Green. I'm not changing my name back to Why So Green because I wanted something that was, if you saw my name on Twitch and you didn't know who I was, you would get an idea of the type of content that I would be trying to do. Can computer engineering solve my crippling depression? Absolutely. However, I would suggest seeking professional help, professional psychiatric help. Computers can be great at looking up methods and so let's see how we can solve depression using computers. So you have depression, you go to Google. What's the steps involved there? Well, you have to be on a computer. So that means you have to have a computer architect that's designed a computer that has a good enough interface for you to be able to use. Then you have to be able to connect to the internet, which means that not only do you need the engineers that can make the infrastructure for communicating over vast distances, you also need network engineers to be able to come up with a way of consistently and quickly transmitting information from point A to point B. Then you need your software engineers to build a search engine like Google, and you need all the data scientists that look at search patterns online that can provide you with the best results. See? This is how we can solve crippling depression using computers. Listen, I'm dedicated to the cause. I'm dedicated. That's why it took so long for the answer. Listen, if we're going to give an answer, we're going to do it right. We're not going to play tricks. We're not going to, ignore a question like that. We can give a real question that's engineering related to something like that. So let's see what we're going to be doing. Let's see what we are. I keep saying gonna. I need to stop doing that. Let's see what we are going to be doing tomorrow. So tomorrow is going to be the first day of crafting a compiler. So what's in chapter 1 of crafting a compiler? Let's see. I actually am not sure. I have this book in front of me physically on my desk. but I haven't used the book. All right, Chapter 1. So Chapter 1's an introduction. We might be able to go over more than Chapter 1 tomorrow, depending how things go. So it's an introduction. It's going to be an overview of the compilation process, the concepts of the plan of building a compiler and the different components, a history of compilers, and the tools for generating compiler components introduced. So I'm sure that, let's see, any books you recommend on Java? That's an excellent question. And the answer is, I don't recommend any books on Java because I don't program in Java. Java does not fit my certain needs. Now, however, in this compilers class, Java is actually one of the more common languages that a compilers class will use. That's a great answer. Yeah. Listen, I had that one. I had the gun in the holster and I was ready to fire. I had my hand on the trigger. Fastest draw in the West. I guess I'm not in the West anymore. I'm technically more in the Midwest to Mideast. Isn't that a shame? It's so humid here now. It's so humid where I live. I would love it. I would love it if it got a little bit drier here. But hey, you can't get everything. Okay. Let's see, what else can we... So, let's see if we may be able to get past Chapter 1. What do we see in Chapter 2? So, a simple compiler. It's... So, they introduce a simple language. That's cool. Then they discuss how would we translate that simple language to another language, DC. We look at some pseudocode, and then they have the complete code and crafted compiler supplement. Okay. We probably could get past those first 2 chapters. There's a lot of stuff in this book, though. I don't know. Hey, what's everyone's background here? What is everyone looking to learn? Is anyone looking to learn anything specific? What time will you be starting this tomorrow? Listen, same time. I got the schedule right below the stream. Give me a follow. That way you can know the exact moment I go live. I will be on time. Do not worry. I will be on time. 7 p.m. Eastern Standard Time. All the way to 10 p.m. Eastern Standard Time. Be there. I look forward to seeing you. So Monday through Friday, it's going to be... Monday through Friday is 7 p.m. to 10 p.m. Eastern Standard Time. Friday, we're taking it back a little bit earlier. We're going to do 5 p.m. to 8 p.m. Eastern Standard Time. Maybe earlier to appease the EU audience, if I am feeling like a benevolent god. 3 hours a day times 7 days a week, a fairly mean schedule. Yep, that is fairly mean, but I only sleep 4 hours a day, so I still have 17 hours to do work a day. It's not bad. I've got plenty of time. See, the thing is, it seems like it's a lot, right? However, what I haven't told you is that all of this is self-serving, because I need to refresh on some of these topics or teach myself some of these topics anyway. So while it seems like I'm taking time out of my day to stream, actually, I'm doing what I would have been doing anyway, and I just happen to be sharing it with the community. Listen, the community is all that matters. It's all about sharing that that treasure trove of knowledge. There's a certain amount of obligation that you have. You know, if you're good at explaining things, or if you have a passion for explaining things, hopefully the skill at explaining things comes. But you know, it's important to pass down that knowledge to people that may struggle. And so yeah, that's the goal of engineering today. That's the goal of the stream. Listen, I want to make the best computer engineers out there. It's all about making the best computer engineers out there. The best educators seem to be those that admit they are learning in the process too. Let's learn together. Yeah, absolutely. So I think most education professionals agree that the only way that you truly know something is if you're able to teach it. Because not only do you have to convince yourself that you know the subject. Kamikaze chicken, my mom was a computer. That's awesome. You didn't say your dad was a computer, so does that mean that you're half computer? Does that mean you're like a cyborg? That's pretty cool. I'm a fan. Listen. Here's a great idea. I've got the best idea I can come up with for growing the stream, for making this the largest stream on Twitch. No, we're not switching to Fortnite. Absolutely not. I don't play video games. I haven't played a video game in 4 years besides Solitaire when my internet was out the other day. I've got the greatest idea. We go to Reddit. I post my stream on every electrical and computer engineering and every computer science subreddit for every university on Reddit. That's the dream. That's the we gotta soak up all those people taking summer classes, right? Or maybe we do the advertising around like halfway through the yeah, we do the advertising halfway through the semester or around like midterm time, that we get all the people that are like crazy looking for help. Yeah, I think, yeah, listen, Livestream Sniper, I think that's a good idea too. I think we're making game-winning decisions on this stream right now. I don't know, do you guys have anything you guys want to learn? Listen, I just chose these books because I have to take a qualifying exam, like I said earlier in the stream, in the fall. So I need to know these topics. Actually every single book that we're going over, I selected as a section of my qualifying exam. The first computers were people and usually female. Yeah, I mean, if you're going back to it depends what you mean by the first computers. Like, yeah, of course, the first people to I mean, of course, before computers existed, people had to do math by hand. But the first, I mean, at least stored program computer, where you talk about a general purpose computer, was in 1946, started in 1944, under a grant from, I think, Pittsburgh and the U.S. Army or Naval Ordnance Division. And that was the EDVAC. I want to learn about you, Dusty Senpai. Listen, if you want to learn about me, you just got to ask me a question. I am 23 years old. I am a PhD student. That was in astronomy. The job title was literally computer back in the day. Yeah, I mean, that's what the movie Hidden Figures was about. It was about all the computers back in the day that would do all the multiplications and divisions and basic calculation stuff that couldn't be automated or was not automated very quickly back then because computers weren't mass produced. Yeah, I know what you mean. Listen, Yune Okapi. Listen, if you want to know about me, you just have to ask a question. Why is Visual Basic the best? Because no other language gives you a pop-up error the second you type something syntactically incorrect. That's the kind of hard-hitting debugging that I need. I need it to completely break my concentration and have to go to the mouse and click OK or cancel on the text box that pops up. That's why Visual Basic is the best. I think everyone in the chat's going to agree with me that clearly the best language was Visual Basic. I automated so much stuff for formatting in Word and PowerPoint and Excel and doing calculations and stuff using Visual Basic, like auto formatting images. What a waste of time. Oh my goodness. I could have spent that time learning getting better at LaTeX. Yeah, listen. I agree. Yeah, LaTeX. Oh, listen, if you want to make those beautiful, beautiful papers, you gotta learn LaTeX. I use Overleaf, actually. I just started using Overleaf. And it's mainly because since I'm a PhD student, I co-write a lot of papers, and the system that we had prior to the current one how did they make papers back in the day, like pre-1999? They still had typesetting programs, didn't they? They still had typesetting programs. Typesetting programs history. Let's look this up. We can look this up on stream. Typesetting programming languages and desktop publishing software. Or in the 70s? In the 70s they did it by hand, probably, right? That's the only way to do it. I mean, that's you're getting to the point almost where they had typists. Okay. Desktop publishing, editing, and layout. Desktop software, Quark, InDesign, PageMaker. Typewriters. Typesetting? Tex? When was Tex? Or Tech? Oh, I didn't know that Tech was written by Donald Knuth. That's awesome. Okay, do you guys know who Donald Knuth is? Yeah, sure thing, Cogasol. I'm happy that you're here. Do you guys know who Donald Knuth is? The guy's a legend. The guy's a Stanford guy. Okay. Donald Knuth. I know it looks like Knuth. It's actually Knuth. He's one of the original computer scientists. This man is a living legend. He is the author of The Art of Computer Programming, an absolute foundational computer science book. He had such an amazing mind, or had. He still does. He's still alive. He has such an amazing mind for combinatorics. Let's see. Yeah, The Art of Computer Programming. This is basic. Oops. It's basically one of the. Yeah, he also co-wrote Concrete Mathematics. Yeah, that's down here. Other works, Surreal Numbers. He appeared on Numberphile. That's not as interesting. I mean, Numberphile is a pretty neat show, but I mean, Concrete Mathematics and The Art of Computer The art of computer programming are far more interesting. Yeah, and a book on surreals. Yep, that's down here. Yeah, surreal numbers. On set theory. No, this man is an absolute legend. The first ACM Grace Murray Hopper Award. He's got the Turing Award, the John von Neumann Medal, Stanford University School of Engineering Hero Award. Yikes. That sounds like a big one. I was going to see if he had a I was going to see if he ever got the Eckert and Mockley Award, but then I realized he's a computer scientist. He's not a computer engineer. So he didn't do architecture. He did mainly algorithms, which is hence why he's most famous for that. How long can you store frozen potato soup? Because I'm about to eat a bowl. It's a few weeks old. It's frozen, man. You're probably fine. If you just say a few weeks old, I would say you could probably store maybe even into a month or two. I wouldn't go much past that, mainly because you're going to start getting the taste of your freezer in there, depending on how well it's sealed. I would guess you could... I'm going to say you're probably fine. Computer File has a video on the start of computer typesetting with Donald Knuth himself. Okay, that's pretty cool. Oh yeah, Computer File. You know, here's an interesting question. So, hitting live, Cogasaw, Une Cappy. I don't know if I'm pronouncing it right. Une Cappy. I can call you Une. I'm gonna call you Une or Une. So here's an interesting question, and it's about number file, whatever the physics one is that's done by Brady, the same people, and okay, it's fine. Okay, cool. Number file, computer file, and whatever the physics one is called. Here's a question: why does computer file have barely any views compared to the other two? Physics, 60 symbols. Yeah, that's right. So why does 60 symbols in number file always get in the millions or tens of millions of views, while computer file doesn't? Physics and mathematics are far more abstract concepts than computers. Now here's the interesting question. Is the reason why it gets so many fewer viewers, like we're talking at like a 10th, but that's not even true. That's not even true. Everybody uses computers though. You say that, so you can't say that like everyone learns introductory physics and stuff, but you don't really learn anything in introductory physics class. Okay, not everyone studies CS. That's true. But there's a lot of topic. Okay, you say not everyone learns introductory CS, but okay, let's take another example. Not everyone learns about CS videos don't become viral. Math and physics attract. Okay, so that's more the point that I'm getting to. So here's what I think. I think that because everybody uses computers, I think there's an inherent bias. You can't lip it. Yeah. You can't fake it as hard with CS stuff because there's so much. The terminology is a lot further away, and it's a lot more strict than in physics. I hate to say that. It sounds like I'm putting down physics or something, but here's the thing. So there are so many things that you could get into with computer architecture, though, that I think would make videos that are just as interesting as any of the computer or any of the number file or 60 symbols ones. I think, here's my hot take on it. So my hot take is that the reason why it's not as big is because people use computers, and that people use programs and software. They don't really think about physics on the day-to-day. And even some people don't really have to do that much math other than maybe calculating a tip day-to-day. There's tons of people that don't even that have to do, that's about it. But even now, you can just press the button on a lot of those auto pay machines where it's like automatically give 10%, right? So I think the reason is people think they know something about computer engineering and computer science because they use computers all the time. That's my thought. That's my hot take on it. That's the reason why it's not as popular. And that's a shame. That's a darn shame. That's my hot take. Okay. Well, any questions for me? I've got a little bit of time. Technically, the stream is, we're coming to the conclusion of another wonderful stream. I want to thank you all for being here. Give me a like, give me a follow. I'm going to be uploading all this stuff to YouTube, like I said. Everything that I've done already is already up on YouTube. But for these last couple minutes, if there's any personal questions you want to ask, I'd be happy to answer them. Have you read the Gang of Four book? The Gang of Four. So what is this? I have not read this book. Is it this? Book. Design patterns? Gang of Four? Is it this design patterns book that we're looking at? Okay. I have not. So what is this on? Elements of reusable object-oriented software. Ooh, I like it. Maybe we'll do a series on this. This would be interesting. I have not read this book. I actually haven't done a lot of object-oriented software stuff. I've done a lot of low-level C stuff, but I haven't done a lot of... I do a lot more C++ now, mainly because I work on simulators. You have to keep in mind that I'm a computer architect, so my computer science knowledge is enough to build a simulator and to hack around with a way to model something that would be physical. So as far as like optimal object-oriented code, I'm not great at, but maybe doing something like this would help me with that. So is it case studies? Case study chapter 2? Okay. Yeah, this is interesting. Maybe we can do something like that. That'd be cool. Okay. What else do you guys want to learn? Listen, like I said, are the things that I have laid out, is that fine? Because, let's see. Yeah, probably. I think most of the views come from strictly casual audience that wants to be amazed by some little fact of which they extrapolate to exaggerate. I don't think you can do that as easy with computer science facts. I don't know. Yeah, probably not. So I can tell people about like transistor scaling and how we're getting down to the level of atoms, which is the reason why we can't make transistors any smaller. And so people can take that and go, it's the end of the world. We can't make chips any better. So yeah, I understand what you mean in that regard. All the popular computer file videos are on passwords and hacking. Okay, this is a hacking only stream now. We're just doing Black Hat Python, right? Number 1, we have to pick an edgy topic, so we'll pick hacking. Number 2, we have to pick the language that everyone learns because you can write print hello and it prints something to the screen, so we'll use Python. That sound good? And listen, I've got nothing against Python. I use Python probably 2 to 3 times a month whenever I need to automate something. But listen, here's the thing about Python for a computer engineer. You can do a project on Euler streams. Yeah, I could. Get chat to help you out. Listen, I need a way to make this more interactive with chat. But here's the problem, guys. This is where you guys are the children are the future. My children. Wait, do you know what project Euler is? It Euler? I don't know what you're talking about. This is something that's new to me. Is this like a computer science thing? Yeah, I know it's Euler if we're talking about the mathematician. Okay. I didn't know because it was programming based math challenges. Is this a bunch of things like the entry round coding interview things like FizzBuzz? It's programming based math challenges. So I mean, is this like FizzBuzz where are there like common ways to filter out people that don't know how to program? Here, let me change it back. projecteuler.com archives. Okay. No, they get harder. Okay. Multiples of 3 and 5. If we list all natural numbers below 10 that are multiples of 3 and 5, we get 3, 5, 6, 9. Oh, excuse me. And the sum of these multiples is 23. Find the sum of all the multiples of 3 or 5 below 1,000. Okay. So they start out at FizzBuzz level, and then they get to actually more complicated or consecutive prime sums. The prime 41 can be written as the sum of 6 consecutive primes. What is the longest prime of longest sum of consecutive primes that adds to a prime below 100? The longest sum of consecutive primes. Okay, so they're math computer science questions. I got it. Listen, I think that's a pretty good idea. Do you want what I think is the best idea? You take advantage of the fact that everyone seems to buy the Cracking the Coding interview book, and you go through that book. I've never even looked at the book. What is that book? Look, it's the first thing that auto-completes. Cracking the Coding interview. 189 programming questions and solutions. Here we go. We have it. We have it. Okay. Yeah, I mean, that's something. That sure is something. No, I think doing something like that would be interesting. Have you tried Rust, our Lord and Savior? Oh, are you actually going to get a pupper? Yeah, man. Listen. So I never grew up with dogs, but I grew up with a lot of cats. And guess what? Cats suck compared to dogs. I've had to like sit for dogs before. Yeah, you have to like interact with them more and you got to take them out on walks and stuff. But when you have a dog, it's like they actually love you. At least that's my impression. Have you tried Rust? I've never tried Rust. Listen, I told you. Okay, do you guys want to know the last video game I actually played? The last video game I actually played was Mass Effect 3. That was the last video game I played for more than like 2 minutes. And it's because I loved Mass Effect. I thought Mass Effect 2 was better. Oh, Rust the language. Okay. I think we were talking about the game for a second. No, I haven't. Let's see. Let's look it up. Rust language. It's a systems programming language sponsored by Mozilla. Okay. Safe, concurrent, practical. Neat. Let's see. Featuring zero-cost abstractions, move semantics, guaranteed memory safety, threads without data races, trait-based generics, pattern matching, type inference, minimal runtime, efficient C bindings. Runs blazingly fast, prevents seg faults, and guarantees thread safety. But what is this used for? Projects using Rust. Firefox. Okay, a cross-platform GPU accelerated it's a terminal emulator. OpenDNS. Listen. Lots of emphasis on architecture. I like the emphasis on architecture. Listen, I'm a computer architect, so it's always going to be slightly on architecture. However, architecture blends in with computer science. You can't have architecture without computer science, because computer scientists, they say what they want to do, and then you have to make what... It's kind of like marketing. Marketing basically says what products the engineers are going to make. A lot of people think that engineers make the decisions of what they're going to make. It's marketing. Marketing says, here's what people want, go make it. Okay, places where you would use C, C++. Okay. Huh. Listen, it already sold me based upon one thing. And that's that, listen, if I see that open source distributed ledger cryptocurrency software project that implements Mimblewimble blockchain is made in Rust, listen, I'm a happy man. Listen, I got it. I solved the riddle of the Sphinx. I know how to take the stream to the moon. Blockchain. All blockchain. All the time. That's it. Listen, I'm going to share a secret with you guys, and it's about blockchain. All it is a singly linked list. Don't tell anyone. It'll make the whole market collapse. That magical technology invented in the 50s. I've got it. We're going to have the NPR teaching streams now. I just need to buy the microphones that are used for every single NPR stream across the nation. And then I need to get the little jingles that NPR uses. Listen, the stream's pretty much over, but we have a little bit more time to talk with each other. Okay. Whew. It's already 10:15 p.m. here. I haven't even eaten yet. Oh wait, I had a protein shake. Yeah, the trouble is finding it at the moment. Yeah, Uncle Bill. So the problem with finding it at the moment is that the only tag for non-gaming stuff, as far as I know, is IRL. And so you can't differentiate between people walking around like the place IRL versus teaching. There's no like teaching section. That's the reason why people can't find it. Are you big? You mean like size-wise? I mean, I'm 6'6". I consider that pretty big. Listen, Kagasaw, you're not gonna die. And if you do die and you curse my stream, I'm just gonna use it for marketing. It's the #1 cursed stream on Twitch. Plays in the NBA? No, man. I played tennis for a university. I used to. I'm a PhD student now. So now I don't have time for anything. I'm huge? Yeah. Tell your friends. I'll intimidate them. I feel it. You feel food? Yeah, okay, Uncle Bill. Yeah, there are community tags, but what do people do when they go on Twitch? So they sort by, they sort by the gaming category, correct? That's what everyone looks at. So they're gonna sort by the gaming category, and the fact that there's no teaching category, there's only an IRL category, means people aren't going to scroll around to try to find communities. I'm guessing that's probably the reason why it's hard to find. Because you have to think about how many steps it takes to get someplace. So if it takes one click to get to the front page streams, they're likely to be visited. Yeah, it doesn't make community searches obvious, so I'm saying that's why it's going to have a hard time growing. So I personally don't care about growth. I'd like growth, but it's not a priority for me. I do this for fun because I like teaching. Okay. Okay. Anyone have any interesting news? What's going on this week? What's everyone doing this week? Anyone have any fun plans? So, I had a meeting with Sandia National Lab last week. That was a lot of fun. They liked the progress we were making on our simulator integration. They are actually flying us out sometime during July to Albuquerque. That'll be fun. That'll be a nice little trip. What else? I'm working on a paper right now. Hopefully get it submitted to either ISCA, which is the International Symposium on Computer Architecture, or ASPLOS, which is, I don't remember what the acronym for ASPLOS is. I probably should. ASPLOS is Architectural Support for Programming Languages and Operating Systems. So I'll either be submitting to ASPLOS or I'd be submitting to Wait, did I say ISCA? HPCA. HPCA. The conference on high performance computer architecture. So I'd be submitting to one of those conferences. Those are both early August. That's on the horizon for me. What's on the horizon for you guys? But eventually maybe we can get an EDU game tag, but Twitch demands we grow first. Yeah, I mean, that's how everything works. Creative had the same hard road before Twitch allowed it. Yep. I mean, that's how everything works. I mean, things don't change unless there's a demand for it. And so you have to write your local congressman. Tell them you want an education section on Twitch. Here's the easiest way. Here's the easiest way. You just have to put out high quality content. You gotta fight for your right to party. The easiest way is you have to produce high quality content. You have to do it consistently, and you have to market it correctly. And the reason why I say that is if you look at the most successful people that do teaching type content or informational type content, you've got I've never watched this stuff, but I think like Eli the computer guy was a very big he was a very big educational guy on YouTube. Lewis Rossman, who's in the same kind of vein, is getting to be pretty darn big now. And you know, I would credit a lot of his. So he's of course doing something. So here's the thing. I watched a lot of his videos. I'm not a tech. I'm not getting into like the soldering business or the tech support type business and the technical engineering type business of, you know, doing chip replacements and board replacements. But I watched him anyway. And why did I watch him? Because he's a charismatic guy. Because he's entertaining. He's got some pretty funny hot takes that he does on things. Make your own platform. There was a hardly difficult guy. Hardly difficult? Yeah, I'm not sure who that is. What is it? Linus Tech Tips? I mean, his is more general audience focus. I don't know what his early videos were, but he still does tech stuff. Know both of those, and it's sad that those have gone into the rant business instead. I mean, it's their platform. They can do whatever they want. I mean, they've been doing that forever, though. They've been doing that kind of content forever. I mean, Lewis at least has been, hardly difficult on Twitch. Okay. I'll check him out. I mean, Lewis has been doing that forever. I've heard him complaining since 2014, 2015 about Apple. Now he has more of a platform, and now he has more sway, and so he can make more of an influence. So, considering it directly affects his business, yeah, I fully support his efforts to try to help his business against what many people would call scummy business practices. I don't know anything about Linus, about his content. I know he does like some cool like PC builds and stuff, and I know they're pretty smart guys. Okay, he was a top programming dude on Twitch for quite some time, averaging 100 viewers, but now he died down since he started to do crypto. What does that mean, started to do crypto? What do you do? What did he just talk about crypto? Are you talking about cryptography, or are you talking about like cryptocurrencies? I'm assuming cryptocurrencies. I don't know how you do cryptocurrencies other than like trading. Unless he's like making his own cryptocurrency. Okay. I gotcha. Interesting. Interessante. Yeah, I gotcha. I know what you mean. Decentralized application. Hmm. Yeah, I mean, so here's here's the thing. If you look at, you really have two options, I think, if you want to make it big as an education streamer. You either have to be doing something that's cool, and I would consider what Lewis does to be cool. Because have you seen the Mike's Electric stuff? The guy is insanely knowledgeable. I have no idea who that is. What does he do? I don't know. I don't I don't keep up with a lot of this stuff. Does he do a lot of like okay, oh, Mike's Electric stuff. Okay. Oh, I'm guessing okay, I gotcha. So he does a lot or what is this? Stop. Stop doing this. Okay, I'm looking at it on the other screen. Okay. Yeah, I know. Yeah, that's pretty cool. I mean, I would do that stuff too if it was still in my area. When I was in undergrad, I would do like a little project like designing some analog or digital circuits. Like, you know, the guy that built the entire, like, what was it, an 8-bit computer with just a little integrated circuits? I did stuff kind of like that when I was in undergrad. I don't have any time to do that stuff anymore. Nor do I really care about that stuff anymore. A lot of that stuff is just reading data sheets and putting things together. Now, there is a fair amount of knowledge, though, that goes into that. And somebody that's a very good, but all the knowledge comes from implementation and implementation type things. My interests lie more in research now. I like to be on the bleeding edge. I like reading research papers to see what architectures are on the horizon. That's my personal favorite thing to do. So here's the thing. So here's my hot take on how to grow a stream. Even though I have a stream that has 18 viewers in it right now, I usually get, I mean, it's gone up a little bit. I started with like 6 to 10. Thanks, Uncle Bill, for hosting me. I appreciate it, man. So here's my hot take on all of that. So you have to do one of two things. You either have to do something cool, like what this Mike's Electric stuff guy does. That's some cool hands-on thing that's going to do something. Or like what Lewis does. Lewis is a double threat, though. Lewis does all the micro soldering stuff, and he's got the cool, you know, microscope, and you know, he's got the not the heat gun, the hot air rework station, and you know, a lot of people don't work with that type of stuff a lot. So seeing something like soldering and how you can make that stuff work is pretty neat. So I don't know anything about the Mike's Electric stuff guy, but I know Lewis is a very personable person. And just from what I've seen, I don't know him in person. I assume he is. He seems like a genuine guy. But you have to go that route, or you have to do something cool, or you have to do something interesting. Or on the opposite side of things, you have to do something, you have to tone it down a ton. You can't teach something super complicated. What you have to do is teach something reasonable. You have to know your audience, and you have to, like the Wall Street Journal story talking about the drones in the warehouse, where it said they use code and algorithms to avoid each other, or so they don't collide, right? That's the kind of level that you need to get into, because people can understand when you say code and algorithms. That just means they do something. Any more than that, then probably going to have a hard time. Okay. Well, I want to thank you all. I want to thank everyone for joining me today. I think we learned a little bit about computer architecture, a lot about what we want to learn in the future. Stay tuned tomorrow. We're going to be getting into compilers. We're going to be talking about what do we mean by compilation? What are the basic components of a compiler? Please send me a message if you want additional content on different topics. If you guys want specialized content, I'd be happy to provide it on the open days and when we have a little bit of time at the end of the stream. If not, that's okay too. Please look down below. Give me a follow. We're trying to build this stream up. We're trying to build the stream to reach as many people as possible. Share it with your friends. Share it with your loved ones. And please, go out there and learn something new. Ciao.